used to be, or is still is, the science building. And this science building is now still there, but it occupies mainly theoreticians and computationalists. You'll see a sports field here. That sports field actually no longer exists and now has the new science building, which is this lovely building here. And that houses mainly the experimentalists in physics, chemistry, and biologists. So it's really a building dedicated to wet labs and not really to theoretical or computational personnel. So this is a relatively new building. The building that the entrance to the university is this structure here. And here it is in close-up. It looks very nice. I've toured many people that come to Georgetown. I bring them to this stately looking building at first. They immediately say that it looks somewhat like Hogwarts, which I don't know if that's good or bad, but there's some similarity with that. Continuing on, I wanted to mention that the university is fairly old. It was founded in 1789, which is quite a long time ago, but not in the grand scheme of the history of India. This is only a few years after the U.S. gained independence. And so here's a nice picture of the winter scene of Georgetown. Some things that may not be known is what it's renowned for. Georgetown is really known for four principal activities. The medical school is huge, the law school is huge, the business school is huge, and of course the School of Foreign Service is a big deal. Many students go through the School of Foreign Service and become leaders, prime ministers, presidents, etc. So one of our alumni, renowned people, there are many, but this is a picture that you may or may not recognize. This was a picture of Bill Clinton when he went to Georgetown University. And he graduated, I believe, in 1968, and went on to Yale University to do his law degree. And he met up with someone. So there's Bill Clinton, and there's Hillary Clinton in Yale University. And of course, we all know what happened after that. Bill Clinton became the president, and he has a tremendous connection with Georgetown University, having gone there for undergraduate studies. And he came to Georgetown many times to give lectures, give state addresses, etc. So I didn't take this picture, but the next picture I took was when Barack Obama came to Georgetown and delivered an address in the gymnasium. So I happened to be lucky enough to be sitting in the second row beside the stage. And so I did snap this picture when Barack Obama was there. And finally, of course, we have Vice President Biden, who will soon become President Biden. You can see from the seal here that he was there when he was still vice president with the Obama administration. But Biden has a long-standing history with Georgetown as well. So I'm sure we'll be seeing him a lot in the coming weeks/months/years. So with that, I thought I'd now turn to the topic at hand, which is more about microfluidics and lab on a chip. And since this is the first presentation of this faculty development program, I was essentially told that there's going to be a wide range of familiarity with the subject. So what I thought I'd do is go through a background of microfluidics, the overview, lab on a chip overview, a little bit of soft lithography. And then I'll turn to my student, Dan, who will talk about some PDMS fabrication basics. Some of you may already have this background, others may not. This will get everyone on the same level. Then I'll go on and talk about the wearable microfluidic chip that we've designed for personalized medicine applications. And then we'll talk about a body fluid collection chip that we're developing at the moment for offline analysis, which is somewhat off topic in the sense that it's not lab on a chip, but it's using microfluidics to take the sample and then transfer it to lab or fluids in the lab. So a little off there, but it's still related to microfluidics. And finally, we're going to look at commercialization and shelf life of such devices. And that'll be just the closing thoughts that we're going to have. And again, these two last thoughts will be presented by Dan. All right, so microfluidics and lab on a chip. We all know that microfluidics, I think, is the engineering of devices. By engineering, I'm referring to the design and fabrication, but which typically handle and process small volumes of fluid. I'm talking the small microliters, nanoliters, picoliters, and even smaller ranges. This topic of microfluidics is very multidisciplinary, interdisciplinary, cutting areas of engineering, physics, chemistry, biology, material science, and biomedical technology, just to name a few. And the fluids, when you're looking at these microfluidic chips, they're essentially being moved for the application of mixing them, separating them, reacting them with reagents, and ultimately analyzing something about that fluid using sensing techniques. So this is what microfluidics does for you. It's, again, handling of low volumes where the length scale that you're looking at in terms of the channels, et cetera, are at least in the micrometer length scale for at least one dimension. Clearly, there could be longer channels, but that's what we're looking at when we're talking about microfluidics. There's advantages that come about when only small amounts of liquid are available, or when you want to conserve or limit the use of fluids. For example, reagents. You may not have a huge amount, and so you may want to limit their use, and so using a microfluidic strategy may be the right thing to do. When you're looking at microfluidics, you're looking at small amounts of energy required to, say, move fluids through the chip. The other thing is that most times the chips are sealed from the top so that there's very little contamination that can occur with your samples. Small size, of course, leads to portability. You can take them along with you. Often, again, no lab is needed because if you've got some sort of sensor readout on the chip, then it can be displayed directly to the user or to for example, for a biomedical device to a clinician. Because of the size scale, again, reactions can be fast. And finally, we can take advantage of some of these microscale phenomena that exist at these length scales. Excuse me. So the field really took off in the 1990s when these microfluidic chips made use of integrated circuit fabrication technologies. That allowed you to use pretty standard and basic technologies that are the mainstay of the IC fabrication industry, but also allowed mass fabrication because you can do batch processing for these microfluidic chips. That's not to say things didn't happen before 1990s. For example, the home pregnancy test, which is a good example of a microfluidic device, came out in 1977, where you used a device, something like this, which would tell you whether you are pregnant or not. So one line would indicate not pregnant, two lines would indicate you're pregnant. And this is basically just a simple assay, a lateral flow assay that is conducted on either a plastic chip or on a even paper chip. And this was the technology of maybe a decade ago. Now, people don't like to read lines, so they actually want to see whether you're pregnant or not pregnant. So this is the more recent type of devices for home pregnancy tests. The other device that makes use of microfluidics came out in the 1980s, which is the self-monitoring of blood glucose using these test strips. Of course, with the test strips comes the use of this electronic readout, which gives you your glucose concentration in either milligrams per deciliter or millimolars. And basically what you do is prick your finger to draw a little drop of blood. And from that is touched on the end of the test strip and is drawn by capillary action into the other end of the test strip, and then is read by the electronics of this readout. And this is a fairly standard process making use of electrochemical detection of glucose. And I mentioned that because a lot of the talk that we're going to be talking about later on is related to glucose sensing. So I mentioned earlier that you can take advantage of the small scale, the physics that's unique in these conditions. And one thing that becomes apparent or jumps out is that surface tension and laminar flow contribute to the complexities of microfluidics. So a lot of times the laminar flow can be a problem because you would like fluids to mix more readily for a reaction to take place. And unfortunately, because of laminar flow, things don't necessarily mix. So laminar flow is exactly that. When multiple fluids are introduced, they tend to flow in straight lines with no mixing. And I've just shown here an application of a blue dye and a yellow dye that come together in a microfluidic channel, and they don't mix at all until, eventually, after a long length scale, diffusion starts becoming dominant. And in the end, they may start to mix, and at this point, it actually runs out of microfluidic space. So out comes this green fluid, which is this mix between yellow and blue. But within the microfluidic channel, there's very little mixing because there's no turbulence. So diffusion is the only way that you can produce this mixing in straight line channels. Of course, people have devised really fancy, intricate techniques to contribute to, or at least to set up turbulent flows within a microfluidic chip, introducing angles, curves, bumps, etc. So these are all techniques to try to get the fluids to mix a little bit better. Again, at these length scales, forces and other phenomena proportional to, for example, volume become less significant. With area, they start to become more important, but really length starts to become more dominant. And by examples, gravity, inertial forces, buoyancies become actually less significant at this length scale. In terms of area, they become more important. So viscous drag, surface charge, friction start becoming more and more important. And finally, length is becoming more dominant. And so that is the area of surface tension. And since surface tension forces are greater than gravity, we then can rely on things like capillary action to draw fluids into your microchannel. And this also will be a recurring theme that we'll be seeing later on in this talk. All right, so fluid transport in these systems can be accomplished, I mentioned before, by capillary action, which is essentially a pumpless flow, but you can also use external pumps like a syringe pump to drive the flow. So this is a non-passive way, but a passive way to move fluids around a microfluidic chip is to use pumpless flow relying on capillary action. So we'll be looking at that a little later on. Okay, so lab on a chip. What is exactly lab on a chip? Well, the name kind of tells you what it is. It refers to the miniaturization of this microfluidic technology that allows operations that normally require lab analysis of liquid samples. And I found this nice representation of a lab where you've got people at different sections of a laboratory doing some analysis on fluids, but that can also be done on a chip scale where you've got analyses taking place at different ports within the chip. These chips, of course, contain microchannels on the surface to transport the fluids for reactions or assays or sensing or product synthesis. And so essentially, you're looking at this traditional lab setting, and I should thank Sanjeev Pashi for these two figures I found. The traditional lab setting, you do things by hand and create your reaction here. On a lab on a chip, you could have these introduced into a microchannel and produce a reaction, sense something downstream from this reaction, et cetera. And when I say product synthesis, I was really talking about this output here. It could be, for example, nano shells containing a drug, for example, or microspheres that contain a drug for eventual drug delivery applications. So this is what I meant by product synthesis. All right, so lab on a chip is usually fabricated on materials that include silicon, glass, polyimide like Kapton. Again, this is going to be part of our conversation of later on about our wearable device. And these are often combined with acrylics, carbonates, polycarbonates, photoresists even have been used as a structural material. Common photoresist known as SU8 is a high aspect photoresist, negative photoresist that's often used with soft lithography, which I'll be talking about. And also there's a new photoresist called Hair SQ, which is a similar product that is very similar to SU8. And of course, polydimethyl siloxane or silicone rubber, which is known also as PDMS. So I've just shown a bunch of images giving you examples of the different types of materials that can be used for microfluidic applications. The first one is by Oak Ridge National Labs, where they've created this microfluidic chip, microfluidic structure in silicon. Elflow has a bunch of pictures which illustrate fluidics on glass. This is your PDMS, looks like it's bonded to a microscope slide to encapsulate it. We have thermoset polymers here, polystyrene thermoplastics, polycarbonates, PMMA thermoplastic, polymethyl methacrylate. A lot of work coming up these days on polyethylene glycol diacrylate or PEGDA, using this material for microfluidic applications, as well as Teflon-like materials like perfluorinated materials, where it limits any kind of sticking, which Teflon is known for. Of course, there's polyurethanes as well, hydrogels, and this polymer, copolymer cyclic olefin, which is produced by Potomac Photonics, is another material. But some materials that are becoming more and more prevalent these days are paper microfluidics, paper-based microfluidics, because of the cost and the readily available resources to make paper microfluidics. Paper works in the sense that it's a very passive way to move fluids around because of the capillary action or the wicking ability of the cellulose fibers in paper. But to wick them in a particular direction, you have to create walls. And so these walls are essentially hydrophobic walls that you can make using, say, a wax-based pencil or a crayon or even an inkjet printer. So this is becoming very popular these days. And because of the popularity, paper/polymer hybrids are becoming more and more prevalent these days. So you've got a paper-based substrate with some microfluidics within the, say, PDMS channel or polycarbonate channel in this case, and you can go on from there. So these are the different types of materials that are available. Soft lithography really involves the process of fabricating, micro or nanostructures using these soft elastomeric materials like silicone. And so because of that, the most ubiquitous is this polydimethyl siloxane or PDMS. And so you have this dimethyl siloxane group that's repeated to make a polymer chain. And this can be used in a molding type fabrication method to create microchannels. And this work really came from the pioneering work in the 1990s from the Whitesides Research Group at Harvard in Cambridge, Massachusetts. There he is. But George Whitesides here, you can see in this picture that he's actually holding his next generation of pioneering work that he's working on, and that is on paper-based microfluidics. So he's done a lot of work, of course, in the PDMS world, but also he's now looking at paper-based microfluidics and diagnostics, as are many, many other research groups. So I'm now going to turn it over to Dan, who's going to talk about PDMS fabrication basics, but that would require, I believe, me to stop sharing and then Dan getting the sharing ability. So I will hopefully stop sharing now. There we go. And Dan, I hope you will get your sharing.
Gosh, it looks like it's all good. So I'll share my screen now. Thank you for sending that permission my way. Once again, thank you to everybody for having me on board as well. It's a great honor to be able to speak in front of everybody. So like Max said, I'll be jumping into some of the basics of PDMS fabrication for microfluidic and lab-on-a-chip technologies. So the standard method for building microfluidics within PDMS is using photolithography, as Max said, invented by the Whitesides group back in the 80s, 90s. And photolithography has the great advantage these days of very, very high resolution microfluidic generation ability. The resolution can go down to the single micron digits, and with proper masking or e-beam lithography, you can get down to the submicron and to the nanometer scale. So that offers even more advanced technologies when you're looking at things like cell division, tumor growth, and such. More recently, 3D printing has really come into the fore as a technology for generating microfluidic chips. It has the disadvantage of lower resolution compared with photolithography, but it, at the same time, with the introduction of two-photon polymerization and other 3D technologies, is moving towards the fore when compared with photolithography. I'll just be talking about photolitho as the main component that we use for fabrication of our microfluidic technologies. And to start, I want to run through how you can make a basic microfluidic chip using PDMS. So you can take a silicon wafer or a silicon oxide wafer, and you spin on a layer of photoresist. Photoresist is a material that, when exposed to UV light, changes in its properties. This is a negative photoresist that, when exposed to UV light, hardens. So you do the exposition through a photomask, which you can see in silver here, and the UV light shines through certain areas. That hardens the material. In our case, we actually use a double layer of SQ50, so that allows for a 3D property with different masks. And so you can use a different mask and form this 3D photoresist mold. This mold, after curing, you can expose it to a self-assembled monolayer of material, for example, perfluorodecyl trichlorosilane, or FDTS. And this monolayer acts as an anti-stiction layer in between the mold and the PDMS, which you pour over the top. So after curing, that PDMS is able to be easily removed from the surface. Now, from the beginning, we used these photomasks in order to expose only particular areas of the photoresist to UV light. For example, these are two different photomasks that we have made within our lab. The first is one that I'll be talking about a bunch today, and that is on the left. It's a photomask that's about a 4x4 inch sheet of glass with holes in it, and a microfluidic design here that you can see could yield capillaries and this large collection port for a technology we'll be talking about later. Because we use two different masks in this process, like you saw before, there are also alignment marks, which are shown in these crosshairs. On the right side is the photomask developed by an undergraduate collaborator of ours, who is looking at isolation of cells and exposing them to different toxins, including metals, in collaboration with the United States FDA. And that works by placing the cells within a reservoir and pumping through different toxins or metal nanoparticles. So you can see the great variation in shape depending on the application. The result of some negative photoresists is you can get very high aspect ratios, that is, tall features with very small XY dimensions. And from the mask that I just showed you before, this is one of the molds that I made in lab just a couple weeks ago. So you can see after exposure, we get these horizontal capillaries and this central collection port. And then these are the alignment marks that you saw. For comparison, these capillaries are about 50 microns across, and I think I used about 30 to 50 microns tall in the z-axis, whereas this collection port is about 100 microns tall. Now, the process for taking your mold and turning that into a PDMS device is pretty simple. It's actually something that you can do at home if you have the right kind of technologies. And all it consists of is mixing of the PDMS. You degas it in a vacuum chamber that removes all the bubbles from the inside by creating a rapid negative pressure on the surface. After sufficient degassing, you pour the PDMS, you thermoset it with the heat, and then you demold and peel it from the SU8 or SQ50 mold. After pulling it off of the mold, you can see you can get multiple devices on one chip, like you saw before with our mask that had 6 devices on one chip. They can be chopped with a razor blade if you're just doing small scale fabrication. That can be escalated to, of course, commercial cutting. And this is the result, the resulting inverted structure in PDMS. When you compare with the SQ50 mold that was shown before, the PDMS structure, once peeled off of it, yields inverted capillary channels that can then be bonded to glass, and a large collection port that we'll be talking about. As you can see, the features are extremely precise. The alignment is simple. You can see there are 2 different layers here with different thicknesses. And so within our clean room facility, that's one of the tasks that's easily achievable. Now, as Mac mentioned, PDMS is normally bonded to glass. That occurs with a plasma treatment. You expose it to an air or oxygen plasma. This creates hydroxyl groups on the surface where the siloxane groups, SiOHs, bond together, the hydroxyl groups are bonded together to form these covalent siloxane bonds in between PDMS and glass. As stated, this is a visualization. You have oxygen radicals within your plasma. These react with the carbon CH3 groups on the surface to replace them with hydroxyls, which can then be bound to other OH groups, forming siloxanes. Lastly, one needs to introduce the fluid. And this can be done traditionally with Lorlock needles. So needles inputted into the PDMS chip and then connected to whatever source of fluid that is needed to pass through. It can also be done by puncturing with a dermal punch and then insertion of a needle tip. The resulting structures have extremely high resolution. You can see here something on the order of 10 micron resolution with very little loss of precision. And these can be related to different technologies, as Mac talked about, technologies in medical and biomedical spaces. For example, medical technologies such as interstitial fluid collection, blood collection, and biomedical technologies such as tumor isolation, cell studies, etc. Because PDMS is also permeable to gases, you can create multi-layer devices through alignment and bonding that allow gas permeation and exposure to cells and components like that in other chambers. So there are a lot of applications that you can do. Now, Mac's going to take over and talk about some of our lab-on-a-chip technologies for personalized medicine.
Dan, thanks. I guess I just got share, okay. right. So before carrying on, maybe I could see if there's any questions or any concerns that people have before going on. So I'll open it up right now for some basic questions on PDMS and lab on a chip.
So, sir, I have a question. Like, is this lab on chip a subset of MEMS or some?
I'm not sure if that was a question, but I could not hear it.
Sorry, sir, I didn't get you.
Huh?
Sir, is this lab on chip one technology or a subset of MEMS?
Dan, can you hear that? Or no?
Yeah, there's reverberation. Someone else is being unmuted.
Yeah. Or perhaps maybe we could just put it on chat, if that's easier.
Sorry. I would suggest that we will have this question answer session at the end, because
Okay.
the number of participants is really very large and it will be difficult to manage if we start taking questions right now.
Okay.
Because I
I
request
agree.
just. Yeah, thank you so much.
Not a problem at all. Okay, so let me then start off with the next part of the talk will be on a wearable microfluidic lab on a chip for personalized medicine. And this is a project we've been working on for quite some time in my lab. Let me get into some of the details there. So we've talked about lab on a chip, but what we're looking at now is biomedically based lab on a chip. And these are typically called point of care devices or point of care diagnostics, where medical testing of some ailment or some disease condition takes place at a person near the site of patient care, whether it be at a clinic or a hospital or at home. But the portability of point of care devices becomes important. And also what becomes important is, since the device is being used on an individual, we're really getting that individual's data. And this is more falls into the realm of personalized medicine. So whenever you make a test using these point of care diagnostics, the corresponding results can be made available to the user almost immediately. But also, if you're connected to the Internet of Things, then physicians can quickly receive that data and make immediate clinical decisions if such a decision is needed right away. So examples of point of care lab on chips include, for example, there's tons, of course, but screening for infectious diseases, forensic analysis at a crime scene, for example, screening for alcohol or illicit opioid usage, something that we're working on, myself and Dan are working on at the FDA. At-home testing for diabetes, I mentioned earlier already, but you can also look at HIV, as well as chemical health panels. When you go to the hospital or a clinic, they draw some blood to look at certain ions and certain gases that are part of this health panel. So perhaps point of care diagnostics or devices will be able to do that more readily and reliably and immediately. Perhaps one day, COVID-19 can be detected, for example, using point of care diagnostic chips. So that would be nice. Most of these chips are really blood-based. And if you're looking for biomarkers using blood-based detection, you can make use of microfluidics, of course. Blood continues, as usual, to be the most popular and physician-accepted body fluid for clinical testing. And part of the reason is that blood circulates systemically, like throughout the body, around tissues and organs, and can collect any metabolic byproducts, any biomarkers from both normal and diseased areas. So if you monitor continuously or semi-continuously any biomarker that may be of interest, you can get any kind of changes or anomalous behaviors related to these biomarker concentrations. But in any of these situations, you rely on sample collection, and that is sample collection through a blood draw as shown here with syringe draw from the arm, or in the case of glucose detection, for example, doing this pinprick or a lancet prick to draw a small amount of blood to do a small analysis. What is critically important here is that once you get your blood droplet or your whole blood, it contains a whole host of things inside of it. And some of the things you really don't want. So what most microfluidic chips or lab chips must do is some sort of sample preparation. If you're trying to find a biomarker in whole blood, often what is required is sample preparation, meaning you must remove, for example, the red blood cells and the white blood cells. So that's one of the big constituents of blood that is typically removed, so that you're looking really at the plasma or serum. After that, you also have to remove some of the waste products like cell debris, but also platelets which help assist in blood coagulation. You don't necessarily need those proteins or cells to be in your blood sample. So those are typically removed. And the removal process can be, active separation. You can have, say, electronic separation or electrical separation. But of course, that requires some sort of external power. You can have passive separation. You can have, for example, diffusion separation. Again, we've talked about diffusion and the fact that long time scales are involved there. So if you want some result that's relatively immediate, passive separation may not be the way to do it. The other thing is you can use membrane integration. That is, put a membrane, a size-excluding membrane within your microfluidic channel to filter out the things that you don't want and allow things to proceed that you do want. Of course, this adds a tremendous amount of complexity into your fabrication process to integrate a membrane into your microfluidic chip. So once all these things are done, then you can continue on with your analysis of finding some kind of biomarker in whole blood. So blood is great, but there are some issues that come to play in terms of sample preparation. And so to alleviate or even eliminate this blood pre-processing that's required, is it possible to use other body fluids? Of course it is. Historically regarded body fluid that's not often used is interstitial fluid, also known as extracellular fluid. Now, interstitial fluid is the fluid that surrounds all of your living cells. It provides the nutrients to your cells and takes away any waste products from the metabolism within that cell. So interstitial fluid, your entire body is mainly liquid and contains this interstitial fluid around all your cells. So that is presents a great advantage over blood, because interstitial fluid, by definition, does not contain any red blood cells or white blood cells, nor does it clot, so it has no platelets. So right away, you've removed some of the pre-processing that's required with whole blood if you make use of interstitial fluid. But we've already shown that it's historically disregarded. And why is that? Well, let's look at a few things. Before getting to why it's historically disregarded, one of the advantages of ISF, interstitial fluid, is that 83% of the proteins found in blood, and these are proteins, biomarkers, et cetera, that are found in blood also exist in the interstitial fluid. Plus, interstitial fluid has its own unique proteins that are not even present in blood. So interstitial fluid can provide a vast host of biomarkers if you are able to get at it. And so it has this tremendous potential as a source for clinically relevant biomarkers. However, it's not often used. And this is the major problem with interstitial fluid. How can you get access to this fluid? To give you an example of what interstitial fluid is, if you've ever cut your finger on a piece of paper, like a paper cut, and it doesn't go very deep, it's still wet. And that's because that's the interstitial fluid coming out from your skin. You may not have gone deep enough to get down to a blood vessel or a capillary, but you've gotten to access the interstitial fluid. So what we want to do, I think I've lost some of my, okay. So what we want to do is try to get at interstitial fluid in a much more accessible, painless manner, not, let's say, paper cuts. And so we've developed this transdermal platform, this transdermal sampling platform for molecules that normally don't diffuse across the skin. And we want to do this in a completely non-invasive manner. And the proof of concept that was used is to sample glucose. Now, we all know that you can detect glucose in blood. We all measure that with the finger stick. But can we measure glucose using interstitial fluid? Well, interestingly enough, the glucose that's in that's in blood actually comes out of the blood and into your interstitial fluid to provide the nutrients for all the cells. So the interstitial fluid does contain glucose, just like the blood, since that glucose is coming from the blood capillaries. So the way we wanted to do this was to create a patch technology capable of achieving this in a truly non-invasive manner, or a non-intrusive detection. And why this came about was interesting. It was a defense application. The U.S. Department of Defense wanted a stress indicator for casualty care. So when you have soldiers in the battlefield, invariably there's injuries. There's people get shot, unfortunately. And how do you assess whether a soldier is severely injured or not so severely injured? If a soldier is shot in the foot, is that something that needs to be taken care of immediately, or is the person that's being shot in the chest need to be taken care of immediately? And so the way that this can be assessed is to look at their glucose and lactate levels at the same time, and that is an indication of blood volume lost. So the Defense Department was looking for a non-intrusive device that will allow the detection of both glucose and lactate without intrusion. So the soldier will just wear this device and it will perform the task. So this was the basis of what this project involved. Clearly, there's a civilian side other than the defense side, and that is in diabetic monitoring. Can we get rid of this idea of finger pricks and drawing blood and using these test strips? Can we get to a manner in which we can use another type of fluid to do the same analysis to detect glucose? And so that was our project goal for creating this transdermal device. So again, I mentioned blood. There's many uses for blood, of course, but it is relatively invasive. You have to actually get a syringe stuck in you and blood drawn out. But there's other fluids that could contain markers: sweat, tears, urine, saliva, breast milk. These are all fantastic fluids, but they all have problems and issues related to interfering molecules, etc. Interstitial fluid is an ideal kind of fluid because it really contains the same stuff, the same constituents as does blood, except for those big red blood cells, white blood cells, and platelets, which we have to remove anyways in our lab on a chip. So interstitial fluid, here's some examples of how interstitial fluid is drawn out. And this is grossly invasive. The first, this example is where a person has worn a device which actually sucks the skin using vacuum and creates these things called suction blisters. And these suction blisters are full of interstitial fluid. And then these interstitial fluids are accessed by poking that blister with a syringe. Now that does not sound very, very nice. It doesn't sound non-invasive. And honestly, if you're going to stick this thing with a syringe, you might as well draw blood. It's just, there's no point in going after interstitial fluid. But why this was done is to look at whether suction blister fluids have the potential to act as a viable fluid for detecting biomarkers that are found in blood. So this suction blister technology came about by this group in 2007. And something that's kind of funny is that they say that the suction blister fluid is obtained by means of a less invasive sampling technique. That's from the authors. And when you compare that to biopsies, yes, but in essence, what you're doing is still, you're attaching a vacuum suction apparatus on the forearm for 2.5 hours to form these blisters, and then you're eventually poking them with a syringe to draw the fluids. Not very non-invasive. So is there a way to better do that? And so what we're looking at is, can we create a device that's more like a Band-Aid that you apply in your forearm or any other part of your body to detect any kind of biomarker? And in particular, let us use the proof of concept of a glucose molecule. And so this is similar to the Nicoderm patch, or these nicotine patches that are often used as a means to stop smoking. The nicotine patch is essentially nicotine introduced into the body through a patch technology. So what we're doing is exactly the reverse of that. So we want to sample biomolecules from the body's interstitial fluid and perform this non-intrusively and through the skin, that is transdermally. Again, this is also a transdermal technology here, the nicotine patch. So we want to do the same thing, except in the reverse direction. So we've got this idea that we want to make it minimally invasive. We want it to be blood-free for glucose monitoring. We want it, of course, to be pain-free. No one likes to be poked with the lancet to draw a little drop of blood. Regardless of how quick it is, you still have to do it for type 2 diabetics 5 times a day minimum, and there is a pain threshold that people do not like to prick themselves 5 times a day. So the pain-free aspect is critically important. And we want to collect this interstitial fluid in a completely passive manner. That is, we don't want to draw this fluid out by sucking it out using a vacuum or any other means. We would love for it to be completely passive. And so clearly, if we're creating a technology that is both blood-free and pain-free, we're going to see a dramatic improvement in patient compliance. People are going to be more apt to test themselves, especially type 2 diabetics, who would rather not have any pain, no blood draws, but have this Band-Aid that tells you what your glucose level is. All right, so how does it work? How does this thing work? And how do we get it pain-free? So let me start off by saying we've already seen we want to sample this through the interstitial fluid, non-intrusively. I'm going to show you, I usually give this presentation to people that know about ice fishing. And I doubt many people in Pune know about ice fishing, but me having grown up in Canada, I've moved to Canada in 1966, so quite a long time ago. I'm used to seeing frozen lakes all the time. So here's a frozen lake. A frozen lake has a thick layer of ice on it, but underneath, the entire lake isn't frozen. There's liquid underneath that ice. So when you go ice fishing is a sport that everyone loves in Canada and northern United States. What you do is go on this lake. It's the ice is fairly thick, so you can walk on it. But eventually you go to a spot and you make a hole. So you're making a hole through the ice, and eventually you get to the lake that is underneath, and you have this liquid that's coming up through this hole to a certain level, and then you get what you want. In the case of ice fishing, you put your hook in and you fish till the fish bites and you pull it out, and now you've accomplished your task. So this is the analogy that I want you to keep in mind with what we're doing. And let me now turn to how this relates to the transdermal approach. This frozen lake, you can think of this ice as the topmost layer of your skin. The topmost layer of your skin is a dry layer of skin. It's called the stratum corneum. and the stratum corneum is about 50 microns thick. So it's relatively thin, and it contains about 10 levels of skin cells that are dehydrated. They don't contain any liquid. And there, if you imagine a brick wall, the bricks are laid out in a offset manner, and that's what the stratum corneum is. The bricks form some of these dehydrated skin cells, and they're about 10 layers thick. So what we would do is come to the stratum corneum or the frozen ice and make a hole in it. And the way we make a hole in it is by using a microheater. So this microheater is contained or is fabricated on the dermal patch on the side that is affixed to your arm. And this microheater is applies a thermal pulse such that it actually creates a hole in your stratum corneum or your top layer of skin. And so how thick is that? Well, it's about 50 microns in thickness, and the diameter of the hole that we create is about 50 microns in diameter as well. And to give you an idea, average human hair is about 50 microns in diameter. So the hole that we're creating in the dead skin, sorry, I called it dead skin. People used to call the stratum corneum as dead skin layer, but it's actually a dehydrated skin layer. The dehydrated skin layer is compromised, and the liquid that's contained here, in this case, it's the lake, but in the human body, it is the interstitial fluid. So now we've got access to interstitial fluid, and we now can get what we want. The great thing about getting what you want is in the case of a lake, the interstitial fluid or the lake itself is here. That is, the level doesn't change. But with the human body, because your heart is beating, it's creating a hydrostatic pressure. And in fact, this liquid comes bubbling out of that hole. So it's almost like a geyser coming out of the hole. And that will continue till, fortunately, the human body is really good at repairing itself. It repairs the hole within an hour. So the hole that you create, which is only 50 microns in diameter, reheals or reseals itself. Actually, I said an hour, it could be an hour and a half to 2 hours. So that will seal up and prevent any more fluid loss. So this is the basic idea of the technology. And people say, well, how can you use interstitial fluid when blood is the standard technology that's used for glucose monitoring? Well, if you look at interstitial fluids if you look at continuous glucose monitors, CGMs, they make use of interstitial fluids all the time. The sensor for this continuous glucose monitor is located here, and looking at a cross section, here's the skin, the topmost layer, and there in the continuous glucose monitor, they insert a needle through the skin, typically in the abdomen region, and they're sensing the glucose, again, in the interstitial fluid. So this is not a new fluid for glucose sensing. It's used in these CGMs all the time. What the CGM has a problem with, in my opinion, is that you are introducing something into the body. And so when you introduce any foreign object into the body, there's going to be an immunoreaction to it. And so suddenly there's going to be, your body is going to try getting rid of whatever is penetrated through the skin. And so this becomes an invasive technique. Again, I will show you how non-invasive our technology is. So I don't want to get into too much detail here, but the key ingredient here to see is that capillaries, which carry the blood at the very ends of arteries and veins, they're not just solid tubes. They actually have pores within their surface, allowing molecules to come out of the fluid through these pores and into the interstitial fluid. So everything in the white here is interstitial fluid. Everything inside this capillary is blood. And only certain constituents of blood can exit through these pores of the capillary. And so really, only the small molecules leave the capillary and enter the interstitial fluid. And it's been determined that anything larger than about 60 kilodaltons stays within the blood. So anything less than 60 kilodaltons molecular weight will be present in interstitial fluid. And if you look at biomarkers that are currently being looked at in blood, most of them are less than 60 kilodaltons. So you would be able to find it in interstitial fluid. Okay. So here I've just shown the exchange of fluids, the use of ISF as a potential biomarker source. You can look for things like glucose and lactate, I mentioned earlier, bilirubin for looking at jaundice in newborn babies, monitoring drugs for efficacy and dosing. These are legitimate drugs as opposed to illicit drugs. You can look for cancer biomarkers, C-reactive protein, which is a biomarker indicative of heart failure or cardiac arrest, or again, monitoring drugs of abuse, illicit or sports enhancing drugs can be looked at using this technique. So I wanted to kind of show you a cross-section of skin here and talk about the stratum corneum here. I mentioned I've said it's dead skin, but it's really dehydrated skin. It's about 50 microns in thickness. You'll see the viable epidermis, which is the living tissue here, and below is the dermis here, containing the arteries, veins. These are the capillaries that come out. And of course, we have some nerve endings, which are just barely seen in the white here, and the hair follicle. So you can see that if you can create a hole just through the stratum corneum, you're nowhere near the nerve endings or the capillaries. And you're able to get at the interstitial fluid that lies within. So here's just a cross-section of the stratum corneum. You can see these cells that are very flattened, pancake-like cells. And so the delivery of therapeutic agents, I mentioned earlier, like the nicotine patch. You have a patch that with an adhesive layer contains nicotine, and it's got some carrier molecule that is tied to the nicotine that can easily penetrate through the stratum corneum without requiring any kind of creation of a hole or micropore, etc. So that is not a problem. Diffusion of biomolecules from within the body to the surface is continually occurring. And here I've shown just schematically these small biomolecules, and some of them actually can penetrate through the pores, the sweat pores, and reach the surface of the skin. There aren't many clinically relevant molecules that are coming out to the surface, which is a problem. Just to give you an idea, if you go out and have a dinner or a lunch with a lot of garlic in it, the garlic molecule can be small enough to actually penetrate through the sweat pores, and you can actually smell garlic on your skin. And that's because the molecule of garlic can actually escape from the capillaries and reach the surface of the skin without any problem. It can easily go through the sweat pore. However, the larger biomolecules that are of clinical relevance cannot penetrate this stratum corneum layer. And in fact, it's a very effective barrier against interstitial fluid leakage, and that keeps the biomolecules of interest within the body. So somehow you've got to break the seal, and I turn back to the analogy of the ice fishing. So we've created a device that allows for this. Here is an array, a sensor array, 5x5 sensing sites, 1, 2, 3, 4, 5, and 5 here. So 25 sampling sites on a chip. We've made these chips out of various materials: silicon, glass, PDMS, SU8, photopolymer. But the main ingredient here is the microheater. So each of these elements has a thin microheater that heats up with a certain voltage, and that temperature that it heats up to allows you to essentially vaporize or thermally ablate the dead skin layer, or the dehydrated skin layer called the stratum corneum, to create that 50 micron pore. And again, we do this using batch fabrication, so we can make 6 patches of 25 sensing sites all at once. And so, yeah, I mentioned earlier that we've made these in silicon, on glass, et cetera. So the engineering flow, I'm just going to really talk briefly where we started. What was the basic prototype of our device? How do we go about breaking the stratum corneum? What is the need for the perfusion fluid? And I'll explain that in a second. And then we looked at enhancements to the patch and where we're going from here. So here's the cross-section of skin I showed you earlier, but with our patch device. And this was the original design. It's a patch cross-section. It's very elaborate, has multiple layers associated with it. But let me tell you right from the onset that this is a complicated device to fabricate. And in the end, we discovered that such complexity is not needed. And which is fantastic, because if you ever want to commercialize something, the less complicated it is, the better. So here we have a cross section of the patch in multiple materials. Here we have a fluid contained within that patch. So imagine a Band-Aid which contains fluid. And why that was needed is when you create a pore using this microheater. So a microheater is here. We apply a voltage to it to create this thermal pulse. The thermal pulse essentially ablates the stratum corneum cell from where that heater location is. Once that happens, we had another layer up here which would apply a potential across this fluid to create, and this fluid was basically water, it was saline solution, which would create a hydrogen and oxygen bubble to push on this membrane, which would rupture. The rupturing membrane would cause the fluid that's encapsulated in that patch to rush out, mix with the interstitial fluid that comes up from within the body, and then applying that potential again would drive the fluid up a capillary channel, also assisted with capillary action, would rise up to a detection layer. And this detection layer was a nitrocellulose layer containing chemistries which would change color that would give you an indication of glucose concentration. So in this case, blue could mean that you've got a normal glucose concentration. And so here I've shown a spent encapsulated cell encapsulation fluid that's already been used up. And here's the next one that will be used up in the next hour, for example. So this was the idea that we originally had, that this fluid, we would need this perfusion fluid, that is something to mix in with the interstitial fluid to give it more fluid to come up the capillary to a detection layer. So to ablate, or this vaporization of the stratum corneum, you need a temperature of about 130 degrees centigrade. So immediately you're going to say, 130, that's crazy. That's way more than what the body can stand. But we apply this temperature only for milliseconds. So it's a very abrupt temperature pulse that we apply to the surface of the skin. And so we made some temperature profiles of these microheaters using thermal simulators. I think you're going to see a lot of talks on simulation with microfluidics. Here we're showing some simulation work with actual structures of the resistors for the microheaters. And then, the theory was validated by in vitro experiments. We used a material called aplograph, which is cultured living human skin. And we essentially, here is an example of the skin where we get the skin and put it on top of our heater with the stratum corneum, the SC, facing downwards, and the viable epidermis above. And we now look from the top and see what happens when we energize the microheater. And so essentially what we do is very crudely focus on the top of this cavity that forms, here, this hemispherical cavity. So we focus on the heater first, so this is the heater in focus, and then we focus on the top of this cavity that forms, and we approximate it to about 40 microns, which is sufficient to actually cause the fluid from the interstitial fluid to come out. So this is well and good. This was some very preliminary experiments. We also did some thermal profiling in 3 dimensions using thermal imaging, using a thermochromic dye, which was impregnated into this aplograph material. And basically that changes color or changes fluorescence based on the temperature that it experiences. And we use this nice thermal imager to look at that. And we looked at that. And so this slide actually should have come before. This is the cultured human skin. This is real tissue, real human skin. And you can see the similarities between the two. Clearly, the topography of the cultured human skin is very flat, unlike real skin, which is bumps and crevices. Of course, there's hair follicles. This has no hair. This has sweat glands. There's no sweat glands here. So this is a very nice in vitro model to use to mimic real human skin. So this is it comes on a 3-inch disc on a gel matrix. The gel matrix actually contains glucose to make sure that this aplograph stays viable for eventual use. And these are typically used in emergency room settings for burn patients where they need to graft some skin onto severely burned patients. So here's where we flipped it upside down onto the heater. Okay, so we looked at the heater, and hopefully this works. You will see we looked from the top using just an optical microscope and looked at what happens when you energize the microheater. And you can see that, I'm just playing this over and over, initially you can see that it's not a clear image, and that's because you're looking through the skin to the microheater. So you can see the little cells that really are the skin cells here, but through that we're looking at the microheater. And once you energize the microheater, boom, it applies this pulse, and you get rid of the stratum corneum layer to a thickness about 40 or 50 microns. So then we did some human testing. This was an undergraduate student who volunteered, so I really call it student testing. And really, this is just to show you the size of this device. Here's his arm, and there's the device. It's a fairly small device. It's hooked up with ribbon cabling or just cabling to a computer. Of course, in the eventual commercial product, this will be wireless technology. And you can see on the screen, he's looking at the little microheaters placed here. Then I decided, okay, we have to test this device. Do we really require this perfusion fluid? How much fluid, interstitial fluid, are we getting when we create this micropore in the dead skin layer, the dehydrated skin layer? So what we did is took a portion of the patch and removed the topmost layer. We don't really need that. And this fluidic cavity, we're not going to fill it with anything. All we're going to do is put the sensing layer directly on top, this nitrocellulose layer that changes color, and we're going to put the edge of it right next to this capillary, okay? And we're going to look at, there's my eye, and we're going to look through a microscope what happens when you apply a thermal pulse to the microheater. And so when you apply this, so what I'm showing you here, this capillary, there's actually 2 capillaries side by side. They're not perfectly square, they're actually rectangular, and that's what you saw on the next screen here. These are the 2 capillaries, here and here. This is the nitrocellulose layer, which changes color. And when you apply a heat pulse, you can keep your eye here. You will notice that we actually get interstitial fluid coming up. And why it's bubbling is because it's actually, the voltage is still being applied. So it's separating into hydrogen and oxygen. And here, the bubble, there's excitement when that happens, so the camera shakes. But eventually, this interstitial fluid begins to wick on this nitrocellulose layer, and this blue color is indicative of the glucose concentration. For me, this was about 100 mg per deciliter, which was normal, thankfully. So the great thing about this was that sufficient interstitial fluid is available once you ablate. When you create this micropore, you get interstitial fluid because it's not just sitting there like a lake. It's actually coming out like a geyser. And so there is no need for this perfusion fluid, this perfusion liquid, and you can eliminate this complexity of trying to encapsulate a fluid in a Band-Aid. Furthermore, you could use now, instead of going to this colorimetric detection scheme where changing color, you can now directly use an electrochemical detection scheme similar, exactly similar to what's used in test strips, except instead of now blood, we're using interstitial fluid. So we find the right enzyme for the molecule of interest. For glucose, we use glucose oxidase. For lactate, you remember that the Defense Department wanted to assess a soldier's severity of injury by measuring both glucose and lactate. So for lactate biomolecule, you can use lactate oxidase. So very similar technologies that you can use this electrochemical detection. So the new layout of this device, we had the same device. We don't need this perfusion fluid cavity or reservoir anymore. And so this can be completely eliminated. In fact, both of these layers can be eliminated. And all we're left with is this. And we actually had made this in SU8, which is that photopolymer I mentioned. So all we have here is now a microheater here. And on the other side, we have our two electrodes for electrochemical detection. But because everything else is eliminated, we do not need the capillary here to draw the fluid up to this color changing layer, and we don't need this reservoir. So all we're left with is this simplicity. Wonderful. This even gets more simpler. Why do we need these things on the other side of the membrane? So make it all on the same side. So the electrodes and the microheater are on the same side, and this will be affixed to the skin. The central microheater will create a hole, a micropore through the skin, and these two electrodes will do the electrochemical detection. So now we have the heater here, the microheater, and we actually, the electrodes that connect to the microheater are intentionally blown. That is, you design it such that once you achieve the temperature, this will become open-circuited. And when this is open-circuited, now you have two electrodes to do the electrochemical measurement. One electrode is modified with this conducting polymer called polypyrrole, which contains glucose oxidase, the enzyme that is used to detect glucose. So this is deposited preferentially on just one of the electrodes. And the other electrode is just a gold electrode. So now one electrode gold, one electrode has the conducting polymer impregnated with glucose oxidase to perform the electrochemical detection. We did some animal studies on this before going to any kind of human testing. We looked at rats. Unfortunately, the volunteers, they had to be anesthetized. They're not dead. They're just put to sleep, and then we shave their bellies. And here's our device on this rat. And we looked at some of the results. I'm going to go a little quicker here. So we looked at standard blood draws and looked at the glucose concentration in blood. And then we looked at, what our device looked at was this, we called it the BIAT device. That's our device. And it follows kind of nicely, not to the same extent. It misses this guy, for example. It's got a bump here corresponding to this increase. And here, we don't get anything. We don't see this. So that was interesting, but there's a reason for that. We also looked at blood lactate. So here's the blood lactate data, which follows very nicely. And here, it does pick up this, at this time point, it does pick up the lactate, but not the glucose. And what is possibly happening is that the stratum corneum is already rehealing itself at this timestamp from when it was ablated to when it starts rehealing. It may not have completely rehealed, but it's now preventing glucose from getting through. But the lactate molecule is much, much smaller than the glucose molecule. So it is still able to escape from to the surface of the skin. So a lot of good things here. The rehealing is evident. No perfusion fluid is required. And so now we're going to look at, so just to compare, remember we said that we put the mouse to sleep. We made use of a standard, very fine gauge diameter syringe to apply the anesthetic. This was the location where the syringe was inserted. It's a 500 micron region where you can see bruising and just discoloration. But in our area where we had our 50 micron pores, there's the skin is still pink. Everything looks good. We also did these on pigs, believe it or not. We had some pig data with both glucose and lactate sensors placed on the pig. And we got some results making use of commercial glucose monitors to act as our control. And so these don't really show a good correlation because, you know, it's kind of flat. But our experiment then continued on to humans, and we actually conducted a very preliminary human clinical trial. This was one of the most exciting things I've ever been involved in. Imagine an electrical engineer in the physics department doing biomedical engineering and standing beside patients who have volunteered their arms and their bodies essentially to test your device. And that was very exciting to me. So here we have our chip. This one was actually made on glass, and glass is not very flexible, obviously, as also the other materials we use, like silicon, will break, it'll cleave on its crystal planes. Glass is not very flexible, but in this case, we use glass because the area of the glass slide was smaller in comparison to the forearm of the individual. So we could just tape these down and attach cabling to get data. And so we did these experiments. We monitored the location of where these patches went. And the 4 dots are representative of that. And these 4 dots were looked at by a dermatologist very carefully, both qualitatively and quantitatively. They were looked at right after the experiment was conducted with these thermal ablation processes, but also 1 week later to see if there was any remnant discoloration, et cetera, that can occur during the ablation process. And it was found that the skin remained very healthy. And in fact, the only issue that came about was the adhesive that was used to place this chip on the skin. This adhesive you can see on the side here, that caused more irritation when you peel it off. It's like whenever you peel off a Band-Aid. It hurts a little bit. And that was detected as the most problematic of this test. So clearly the most important aspect of this test was to understand whether the technology is in fact pain-free. It is definitely blood-free. We did get measurements that correlated to glucose, which I'll show you in a second. But you cannot ask a rat or you cannot ask a pig, do you feel any pain? But these experiments allowed us to do that. We could ask the individuals whether they felt any sensation when a ablation process occurred. So some data, I'll just show you some really quick data. Our device is called the Sweet G. And again, I want to point out that this was our first real foray into doing a clinical trial. And we were so excited by this, we did not optimize in any way the sensor. The thickness of the sensor, the dimensions of the sensor were not at all optimized. But looking at the data, we did a glucose challenge, meaning we fed the volunteers high glucose liquids and then started our monitoring. And this was done with an off-the-shelf AccuCheck monitor using finger sticks. And you can see the trend here related to our device, which was the Sweet G. It followed quite nicely, and we were very excited by this. We also made use of the YSI Yellow Springs instruments, which is the gold standard really for measuring glucose and other biomolecules in blood. And so we had the same glucose challenge. This is the same data. The yellow is the same data as this one, but this just shows our device with respect to the Yellow Springs instrumentation, which is in pink here. And again, the interesting thing is that the peak here for the gold standard occurs at this timestamp, whereas ours occurs at this timestamp. This is a known delay that is often seen between blood glucose and interstitial fluid glucose. So that even corresponded well with what is known in the literature. Okay, so now I'm turning it over to Dan. Surprise, Dan. We're going to talk about, in general, body fluid collection based on this device and commercialization and shelf life. And one thing I do want to point out is this lab on a chip idea. You can have different complexities of lab on a chip. Clearly, our first iteration of this device was more complex than it turned out that needed be. But again, simplicity has worked to our advantage. And in fact, this technology, it's a patented technology, and the patent has been licensed to a company based in the United Kingdom for its commercialization. So now I'll turn it over to Dan. I'll stop sharing my screen, and he can continue on through the.
Thank you. And when able, I can share my screen. Just wait on that. Great. Thank you. I know we only have probably 5 minutes or so to go over what I have left, so I'll try to breeze through that.
Is that our time limit here?
Is that 12:30? I'll just run with it. Kick me out when needed. So, as Mac mentioned, the clinical trials were conducted with a glass-based device, and we want to move away from that because of cracking of the device and the rigidity, as well as some issues that were caused with inconsistent volumes being found at the sensing electrodes across the device. And so we moved on to a device made with two different polymers, namely PDMS and Kapton. PDMS is a siloxane-based polymer, and Kapton is a polyimide. PDMS here was used as the microfluidic layer, and Kapton contains the metallization and the entry ports for interstitial fluid to enter into the device. In brief, the interstitial fluid is collected with heat pulses, as Mac discussed. It can then enter into these capillaries into a main collection port, where it can be used with offset analysis or on-site analysis with sensing electrodes on top of the Kapton. This is a picture of one of the Kapton layers. I know I've talked about the PDMS fabrication already, so I thought I'd show you this side. Kapton's a soft, flexible polymer. You can wave it around. It'll reform to its own original properties. It has that elastic properties. And just like the old device, or like the old version, we can fit 6 devices on each wafer. One device is a 5x5 pattern with microheaters. On the right here, you can see there are 4 microheaters per entry port. That allows for a greater volume of interstitial fluid to be collected. And down here is a pretty low contrast SEM image, but it shows the relative size of the capillary hole to the microheaters. Now, I imagine you're thinking to yourself, well, the key is you have to bond now PDMS to a Kapton layer. And that's done through a 2-step process, or really 3. The Kapton and the PDMS are both hydroxylated through an oxygen plasma, then introduced with a self-assembling monolayer of materials called GPTMS and MPTMS, which are then bonded together under pressure and heat. You can see when there's proper bonding, the PDMS undergoes cohesive rather than adhesive failure. That is when you try to pull it off of the Kapton layer rather than peeling, it tears apart in itself. So that's how you know you have this good bonding. On top of that, the layers needn't just be stuck together, but the microfluidics need to be aligned. So you have to align these capillary channels in the PDMS with the vertical capillary ports on the Kapton. And so we do that in our clean room facility using an alignment stage. And this was developed by a grad student at Georgetown. It consists of 2 different stages, which can be rotated and translated to align up those 2 layers. So this is the result. 6 of these devices. I like splitting it in half and doing the alignment with 3 devices at a time. That's why it's cut there. And this is one of each device. So you can see flipped over with the gold metallization on the Kapton and the PDMS microfluidic layer on top. As we know, this is replacing a needle-based technology, and what we're looking for is accuracy, a long shelf life, and reusability or disposability. So the long shelf life is extremely important in that when you generally make hydrophilic structures in PDMS, you use an oxygen plasma treatment. And this hydrophobic recovery is actually demonstrated beautifully by the next speaker, who you'll have on in a few minutes. So Dr. Bodas had a great paper back in, I think, 2007 on this. And PDMS has to be hydrophilized because passive microfluidics, if you use microfluidics without any actively driven pumps, are reliant on capillary pressures to draw fluids into the device. And this long equation shows you that the capillary pressure is dependent on the cosine of the contact angles. That is the angle that a droplet of the fluid will make on the surface. And so you need a very hydrophilic material in order to draw fluids into the device. So we did a bunch of work on long-term hydrophilicity with different techniques, whether it be oxygen plasmas, roughening, metal oxides deposited on the surface, plasma polymer grafting, and most importantly, and what we used in the end was a surfactant addition. So a surfactant is a molecule that has 2 different ends. It has a hydrophilic end, generally a polar oxygen group, and a hydrophobic end. As you can see, that can be a siloxane-based group or one with this hexane chain. And what happens is, over time, when you place these surfactants in the bulk of polymer and place water on top, the surfactants diffuse to the surface, lowering the surface tension and causing the molecule or the drop to spread over the surface. We did some characterization in a recent paper in JMEMS and showed how the contact angle evolves with the square root of time, and you can extract some information about the diffusivities of these polymers in the matrix. The result is that we get these quick, functioning, and long-lasting devices where you can optimize the surfactant that you use in the matrix to cause the quickest and most effective hydrophilization and therefore capillary pressures, in turn the quickest functioning devices. And so Mac, if you just want to talk about any conclusions here. I assume you can talk.
I really didn't want to talk too much about conclusions. Okay. There's still some things left to be done. One thing that is critical is to look at whether we can use this technology and go back to our crazy idea of encapsulating fluid, but rather than a fluid to perfuse the micropore, can we in fact put a therapeutic agent into that reservoir so that we can do drug delivery through the skin? This is a goal that we're striving for with a group at the Georgetown University Medical Center. looking at drug delivery for Parkinson's disease and for Alzheimer's. So this is something that's coming in the future. And so I don't want to say conclusions because this is still all a work in progress, but here's some highlights of what we've got. I'm not sure how much time was left, but I think we've got time for plenty of questions. So I'll turn it back over to Dr. Bowie.
Thank you very much. It was a fantastic and very insightful work, and I'm sure that as I enjoyed this, everyone in this group has enjoyed and is thrilled by it. And I think now I can start with the questions that are asked on this chat of this group. So, first question is this LOC a different technology altogether, or it is a sub branch of MEMS technology?
So I would say, I would say that this technology is a microfluidics and MEMS technology, but it started out as being something far more complex than it needed to be. And I think perhaps this complexity would be reintroduced when we think about drug delivery applications. In the sense of lab on a chip, we're not really doing analysis, reagent mixing, etc. So it's not necessarily a full lab on a chip like I showed in the schematic of different components of a lab being, the fluid being passed around through channels for analysis and mixing, etc. It does not have that component, agreed. But this is more of a microfluidics and MEMS technology.
Okay, next question is, did you perform histopathology studies after the blasting?
So we looked at, the dermatologist that we had on our team looked at the skin quite closely with just qualitatively, but also quantitatively, using a technique that's often used, using a vepometer. That is essentially a measure of the skin health. And from that, there was very little trauma that the skin endured during the process of ablation. We did not do any histopathology.
The recovery time of skin cells. What is the recovery time of the skin cells after the ablation?
So after ablation, it's about 1.5 to 2 hours that the skin cells start to replenish the stratum corneum. So eventually, when we commercialize this device, users will ask to keep the Band-Aid on after they've performed their last sensing action for at least 2 hours to minimize any bacterial intrusion through the pore that you've created.
Okay. Good morning. I have a question. Can we use microfluidics for gaseous fluids as well as the liquid fluids? Can we exactly use the same technology for the, say, volatile organic compounds?
Dan, do you want to take that since you showed that image of the gas and fluidic channels?
Yeah, so gas fluidic should be doable. One concern with using PDMS is that it's permeable to gases, and so if you want to do gas fluidics, you would generally have to do that with silicon or glass fluidics, which would be done with micro machining rather than mold and thermosetting with polymer. But yes.
I can ask one more question. Yeah. So you mentioned that sweat does not contain any biomarkers. However, there are few studies. Yeah.
Sweat contains many biomarkers.
Yeah. So you never thought of using that as a detection tool, for example, instead of these heaters and yeah.
So partly because sweat is a local phenomena, whereas blood, just like blood, interstitial fluid is a systemic fluid. So it will be capturing biomarkers and biomolecules from throughout the body, just like blood. Whereas sweat can be more localized, plus it has some issues with cross-contamination. But that's not to say sweat is not usable as a fluid for biomarker detection. Many people are doing that.
There is one more question. Have you used any chemical sensors into subsystems?
I'm not sure I understand the question. So a chemical sensor with this transdermal technology?
Yes, in such type of system. For
Well,
example, when the liquid comes out, I mean, IFS, intra, whatever it is. So when it comes out and it gets ablated, so whatever is remaining, you test it by your electrochemical methodology. So
Correct.
is there any purely chemical sensors that can be used? I think that is what the person wants to ask.
I see. I mean, we've looked at trying to do this Chem 7 panel, like a chemical panel. One ion that we've been trying to get at is potassium. And so for potassium detection, we used the ionophore technology. And one ionophore we used was called validomycin. Validomycin bonds specifically to potassium, but it also has interference with sodium. So there are ways to get around that, but that's the only kind of chemical detection we've done. It's not really chemical, but it's ionic detection, if you will.
Ionic, yes. One more question. Are there any allergic reactions in the process of that you have noticed in the epidermis layer?
No, again, the dermatologist took care of that by looking at the skin's reaction to the ablation process immediately after the trial was done, but also 1 week later. So if any kind of issues were to have occurred, they would be occurring during that stage, and no bad effects were noticed.
Okay. We will take just one question now. I think if there are any other questions, I will email them to you if anyone is that much interested.
Sure. Absolutely.
One question is, what is the status of the commercialization for this technology of yours?
So the commercialization, the company, they sponsored this clinical trial in the sense that they provided the funding because they liked the technology, but they wanted a little bit of reassurance that in fact it is pain-free and in fact you can get a glucose measurement without any blood. And so once this clinical trial ended, they were happy, and then they essentially bought the technology from Georgetown University and have now continued from that point. The technology does not necessarily restrict to glucose detection only. So the commercialization right now is geared towards alcohol detection as well as cardiac infarction. So these are two areas that they're looking at for using interstitial fluid. The company has manufacturing in place in Japan, and so devices will be manufactured offshore in Japan, and that's the stage we're at still. They're not going to be commercialized in the very near future, but in the future.
That is really something that we will be looking forward to. And I again wish to thank you, because I know that it is by now the midnight in your place, and you have been very generous with your time and your attention for our FDP. And both of you, you and Dan both, and I heartily thank you from coordinators as well as the participants. Thank you very much, sir.
Thank you, sir.
Thank you.
Thank you. Let me also give a quick shout out to Dhanajay Bodas, who there he is.
Hi, how are you, Mac?
Good. How are you doing? I think he was the one who suggested or put forward my name to give this
Yes.
presentation.
I would thank him. Yes.
So thanks a lot, Dhananjay. We have quite a history going back. I used to visit Pune quite often, and really Dhananjay would take care of me. make sure I never got into trouble.
Dhananjay is our colleague and a good friend, actually. We have also worked together.
Excellent, yeah. This was when he was a graduate student that I know.
Yes. So let us welcome our next speaker, Dr. Dhanajay Bodas. Let me again introduce him. Dhanajay is a PhD in electronic science from University of Pune. Before joining University of Pune, he did his master's from MS University, Baroda. Presently, he is working as a scientist at the Nanobioscience Group in Agarkar Research Institute, Pune. He is also adjunct professor at the Department of Instrumentation and Control Engineering at Cummins College of Engineering for Women. Dhananjay has got 11 research projects completed as PI or co-PI. He has published more than 70 papers in international journals of repute. He has filed 10 Indian patents. Dhananjay has, through his career, gone through lot of achievements. In 2015, he won Alexander von Humboldt Research Foundation Return Fellowship. In 2014, he won Young Scientist Award from Institute of Smart Structures and Systems. He won Alexander von Humboldt Research Foundation Fellowship in 2006. And he was a postdoctoral fellow. His fellowship was awarded by French Ministry of Research for the year 2004 and 2005. Dhananjay is life member of Humboldt Academy, Pune chapter, and he is also life member of Institute of Smart Structures and Systems. Apart from what he has written, let me add a few sentences of mine. As I already said, Dhananjay is our collaborator, and also because of his unique set of expertise, he is the expert member of our project committees always, and that is how he is always closely associated with our institute. So now I welcome Dr. Dhanajay Bodas, and I request him to continue with his lecture. I think he had logged out. He's joined again.
Hello.
Dhananjay, switch on your video.
I have. Are you able to see me?
No. Yeah. So now I will transfer the control to you, and you start your presentation.
Okay. Great. Thank Okay. So are you able to see the screen? Yeah. Is the screen visible? Hello.
Unmute kar. We are seeing that you are starting to share your content, but not able to see the content yet.
Okay.
Link is slow. Link is slow. Dhananjay, can you just remove it and then load it again? Probably it's still not like a. Hang हो गया. हाँ.
Yes, sir. Yes, sir.
आलं. Now it has come.
Okay, but I am not able to see my own screen. Anyway, are you able to see the full screen or just a?
We can see your screen. Yes. No, it's not full screen. It's like a screenshot. It's in presentation mode. No, not in presentation mode. Editing mode. Make it in presentation mode.
आप ठीक हुआ अब हो जाएगा वो भी हिलने लगे ना वो भी
नहीं ना वो भी.
I just stopped the.
Now it is. Yes. Now it is fine. You can start.
Is it visible in full screen or it's just the half screen?
full screen.
No, it was visible. Now it is again gone. Probably you can start. It will be visible. हाँ.
अपने प्रॉब्लम
I can see it, by the way.
Hello, Dhananjay. I think you can connect again or something. मैं कुछ नहीं कर रही. पर अभी तो नहीं Dhananjay, stop your sharing and share again. मी त्याला लिहिते थांब. त्याला फोन कर.
हाँ अभी फिर से चलेगा अब आएगा
मैं उसको बोलती हूँ स्विच ऑफ युअर व्हिडिओ. तुझा स्क्रीन फ्रीज झालाय तो पुन्हा हे कर. बंद करून चालू कर.
अभी दिख रहा है
हा यू आर विजिबल. त्याचा माईक ऑन कर ना.
Can you just share? I mean, allow me to share my screen again.
हाँ. Yes. Make him
प्रेजेंटर बनाओ ना आप
अगर ये नवीन
नहीं आपने दूसरा बनाया अब बनाइए यस
हाँ.
दूसरे लॉगिन
Yes. Try again.
Yeah.
स्पीकिंग
Left the meeting. Dhanajay Bodas.
No, I am here.
दूसरे से
Okay. You had 2 logins then, I think. Okay, start now.
Is the screen visible?
No, not yet. Dhananjay, otherwise switch off your video and then share. If your connection is weak, yeah.
आ गया अभी
Now it has come.
So, is it visible in full screen mode or it's still in a half screen mode?
Half
Is it
screen.
visible this, clueless about this.
पण आधीचं नीट झालं होतं म्हणजे हे तुझंच आहे बरं. हा झालं. नाव स्टार्ट.
नाउ स्टार्ट
Okay, sorry for the glitch. Very good morning to all the participants as well as the coordinators, and a big thank you. still continuing. So currently working as a scientist in Agartha Research Institute, um, and working on various topics of microfluidics, microreactors, and so on and so forth. Thanks, Mac, for excellent presentation and to gear people, the audience, with MEMS and various different fabrication techniques. It was pleasure working with you. I really appreciate the long years of collaboration as well as consistent mentorship which you have shown. Thank you so much. Yeah. So this is the work which is related to biosensors, taking forward from what interested is looking at bacterial detection and bacterial pathogens. About. So just to gear up, we are really short of fresh water. Depleting, and that's where I think becomes very important. And how we are, not only how we are using it, but then we should be able to preserve whatever is left. And if we are polluting whatever is left, I think there won't be any more freshwater lakes left for our next generation to drink. So this is what generally we see in news almost every year. This year is a special year for diseases, especially in terms of corona pandemic. It's not only corona, but then there are a lot other diseases are much rampant, much dangerous, which are kind of not very looked at. Only when it comes in news, we really take care of, or maybe we have certain alarming responses with these kind of infections and these kind of diseases. But by and large, probably we have adjusted to these kind of rampant killings of bugs. Only when there are some news like super bug, super run rampant, killer outbreak, so on and so forth, then we generally give an attention, but then this is a very short-lived attention. So what is essential in these particular cases is a very long-term research goal, and these are unmet needs which needs to be fulfilled in terms of detecting these kind of bugs which are really dangerous, even more dangerous as compared to corona. I think corona currently recovery rate is around 94% in India, and the death rate is really less than 3%. So though it is spreading far and wide, then the fatality is less. But with these bugs, the fatality is quite significant, and that's where I think we need to really focus our resources for detecting these kind of diseases. And that is exactly the response what we have once there is an infection. I think I'm very sure that WhatsApp universities will be publishing these kind of reports very soon in terms of corona too, once we are out of it, once the vaccine hits market. That is few reports here and there, few journals would cover these kind of reports, and probably that's about it. And nothing much is done until the next kind of invasion occurs, and then we again start thinking about these kind of diseases and cure as well as diagnostics in terms of these kind of diseases. So what is the necessary response to all these things is detection very early, as Mac was kind of projecting in very low volumes, low infections, there's low amount of infections. If we could detect these kind of diseases, I think it becomes very easy to cure, as well as even to prevent in certain cases. So that is the reason why MEMS as well as lab on a chip technologies are kind of taking the world by a storm. Though they promise so much, there is very less commercialized because of lot many reasons related as well as unrelated to the technology. So again, as coming back to the response of what we generally do is we try and focus on the detection techniques. We kind of master the conventional techniques, but then what is really essential is rapid detection technologies, and that is where I think there is a lot of scope for research as well as development in commercial space too. So currently, once there is a bug detected or bug known, there are three major techniques, that is three classes, which is culture-based techniques, immunological methods, as well as molecular methods, which can detect bacterial infections. But then if you compare all these techniques, let's say, for example, you have a plate and you have bacteria, you grow bacteria and then detect after 24 or 48 hours of growth. These are very time consuming. When you come to molecular methods as well as immunological methods, they are not so much time consuming, but they really hamper in terms of sensitivity of the detection, or they are really expensive. So what becomes the imperative is to have a technique as simple as pregnancy detection, which could be used by any consumer. I think that becomes an very big advantage in terms of technological innovation whenever we are talking about such kind of simplistic devices, simplistic technologies, which could be used by a user who is a layman. That is where I think this technology also would be heading towards. So to take out all these aspects in terms of time consuming, expensive, laborious, as well as requirement of skilled manpower, what we could do is we could build some devices or build techniques which are rapid, which are sensitive, very specific, cost effective, and portable, because that will give us the edge. And that's where it brings me to these different criteria which are required, or which are extremely imperative when we talk about these bacterial infections. So what we require today is not only techniques which would be able to detect, but then the detection should be rapid, it should be highly sensitive, it should be reliable, device or technology should be portable so that it reaches anywhere in fields, it should be robust, the technology should be reproducible, cost effective, easy to use, and if we can detect multiple pathogens in using a single chip, I think that becomes a easy or effective solution for detection of these kind of killer bugs. So the solution to this problem is nothing but integration of various fields. As Mak was telling, he is a physicist and now working with doctors in a hospital. I think my story is kind of similar when it comes to the integration part. I also hail from physics and now working in an institute which is primarily based on life sciences. So I think this becomes an extremely good mix of different disciplines where we would be able to then think about devices, think about technologies which could really serve where the need is. And that's where I think integration of biotechnology, microtechnology, and then integration of different kind of systems, that is merger of branches, which will lead to the only solution which will be possible. So what is then essential is to create a biosensor which would use different kind of materials, different kind of things, which is then going to build a particular highly portable, highly sensitive, as well as highly specific biosensor. So what we are targeting is to detect Salmonella typhimurium in this particular case study. We are going to use a recognition element as a phage. We are going to use magnetic nanoparticles as well as quantum dots for this particular purpose in a microfluidic chip, which would then give us a sensor which is highly interdisciplinary in nature. A lot of research has gone to build this kind of a biosensor. And that is where I'm going to touch upon each and every aspect in this whole presentation of 1.5 hours. So this becomes a highly multidisciplinary field where in my lab, Biomina is working. We have physics, chemistry, life sciences, as well as engineering disciplines working in the lab. That's where I think we would be able to create some fantastic technologies as well as devices which could be highly application oriented with having sound basic science. So this is what we are aiming at, to create a chip, that is a microfluidic chip or a lab on a chip, wherein all the processes which you generally do in a lab, which even Mac was talking about filtration, about pumping, about liquid handling, about reagent consumption, all these things, if you could do in a highly sophisticated chip, which is known as microfluidics or a lab on a chip. So can we really miniaturize to that extent? And the answer is probably yes, as you have already seen in the first lecture, wherein we would be able to provide integration not only in terms of liquids, but in terms of electronics too, because you all are aware that electronics, that is the MEMS industry, was originated from silicon industry. That was somewhere back in 1955 to 60. IC technology was pretty mature, and thereon from 1980s onward, silicon, when it was established that silicon could be used as a mechanical material, the technology, or say the joining hands of electronics as well as mechanics happened, and the whole technology was then based on silicon. That is silicon as a electrical material, electronic material, as well as silicon as a mechanical material. So that's how the acronym MEMS came into picture, which is micro electromechanical system. So the devices were smaller, which took fabrication techniques from the IC manufacturing technology, and then which use property of silicon as a mechanical material to build sensors, actuators in application areas varied as mechanical, thermal, biological, chemical, as well as magnetic. So that is where I think all these applications emerged from. And then later, somewhere in 1998 or 2000, early 2000, there was a spin-off. There was kind of a breaking from MEMS, that is silicon technology, and polymers got introduced. And nowadays, more and more polymer materials are being used, as you have seen, Kapton, PDMS, PMMA, which Mac showed in his presentation. So why it is imperative to work on lab on a chip is because we can do not only manipulation, but control of lot of reactions. As heating was shown, as controlled heating was shown in the earlier presentation, we could actually control a lot of fluids, a lot of reactions, lot of reaction rates when we are working with these kind of smaller devices. So it is not only manipulation becomes an integral part, but then what is essential is control of various reactions. That becomes very simple when it comes to lab on a chip technologies. Now, why this happens is because of its obvious size advantage. What we are working on is less than 100 microns, and when we are working with such low volumes in such sizes, volumetric effects are really low as compared to surface effects. Now, surface effects dominate, and that's where you could see laminar flow conditions in microchannel. So what we could do is we could incorporate a lot of small molecules and then study the reaction rates, and at a very low level, low scale, and that's how we would be able to study without any deviance or divergence in terms of its bulk synthesis. So that is where I think these lab on a chip techniques are being researched more and more, and people are trying to fabricate structures by various different techniques. So what are we actually talking when we talk about lab on a chip? Are creating a very small, tiny micro channels, which are of the order of let's say 100 or so, even less in many cases. What we could do, we could then mix liquids at precise volumes, precise temperatures. We could build reactors, as well as we could have analytical tools to assess all these parameters which are essential. And when we integrate all these different kind of passive as well as active components onto a simple chip, it becomes a system, and that is what a lab on a chip is. So it generally leverages lab on a chip when we talk. It becomes, because it's a lab, it generally tends to use fluids. Now, fluids could be gases as well as liquids, where I think somebody in the earlier presentation asked, can we use gases? Yes, the answer is really yes, that we can use gases as fluids, because gas is nothing but a rarefied fluid. So wherein we would be able to study different kind of fluids in different kind of channels, wherein we would be able to then manipulate reactions, its mixing at micrometer length scales. So it is kind of a box wherein we would be able to do a lot of magic tricks. just to highlight this particular point. So what we are doing is we are really working with a lot of small volumes. When I say small, we can go up to femtoliters. People have gone up to femtoliter volume from starting from microliters, which is extremely small volumes. Now, this small volume has, as I said, it has its own advantages as well as disadvantages. Advantages are many. They always supersede the disadvantages. The disadvantages is only when you try to translate these micro reactions into bulk scale. So when you want to kind of produce in bulk, then there is a serious disadvantage of this technology. But then if you could do work with, let's say, a few microliters, a few nanoliter volume, I think if we are getting similar kind of results with small volumes, then we really don't care about the bulk volumes or bulk reaction rates. So small size is an extremely handy tool or an advantage. Now, what happens is what comes along with small sizes, it's low energy consumption. So all these tools could be then thought about working with renewable energies like fuel cells or even hydrogen storage cells. And then what we could do is we could study a lot of interesting effects in micro domain, because there are a lot of things happening in micro domain which we generally tend to ignore when we talk about bulk reactors. Then there are a lot of devices when you think about micro size, and when you compare our body structures, I think then you could easily relate these tiny devices or tiny sizes to many other body organs. One example is the drug delivery tooth sitting inside our mouth. So what happens is you can kind of match the sizes, and then if once the sizes are very small, then you can think of embedding these kind of technological innovations, tiny devices into our body. Pacemaker is for sure an example which everybody would be aware of. So this is nothing but a drug delivery, a teeth which actually sits inside our mouth, and then it repairs these cavities, or at least relieves us from the pain. When there is a very excruciating pain, there is drug which is released, and then that's how you are even don't know. These are like so ubiquitous technologies wherein these function almost automated. So another example is a very tiny speaker which uses bone conduction. Now the same kind of Bluetooth speakers or headphones which we generally use, earphones which we use, and there is a problem with the eardrum as well as the ears in typically. So what happens is these kind of tooths where they can be actually fit into inside of the jaw, and they can be used for bone conduction. That is, you could listen to sounds, very tiny sounds, using bone conduction technique rather than having these bigger devices into the ears. Especially these kind of devices help for elderly people wherein they are very uncomfortable wearing those devices. So this is one example of small size. Small size comes with, as I said, low energy consumption. So this is an example of low energy consumption, which is an electronic fountain pen. This is not a mere fountain pen which we generally use. So what happens is we can do very precise volume delivery using these kind of fountain pens. So if you want to take shots of insulin in case of if you are diabetic, now these kind of pens will help you to have metered doses of whatever drug which we are having. So it could be intravenous or subcutaneous injections. If you want to have these kind of fountain pens, could be used in those cases to have metered volume of drug injected into our body. So studying the effects of micro domain, this is the famous picture which was published in Science magazine in the year 1999, I think, from George Whiteside's group. From where I think the microtechnology, or say microfluidics per se, was into the research. So this was a typical picture which shows laminar flow condition, wherein you could see at a smaller scale, which is around 100 micron, all the liquids do not mix, they just flow side by side. So that is where I think it's pretty intriguing, pretty interesting work with these kind of liquids, wherein you could have lot of reactions. We could think of lot of juggleries, magic using these kind of technologies. So this is an example of a laminar flow, how the liquid moves side by side without mixing. So you could see the yellow and black liquid are moving side by side without mixing for a very long length. And maybe at the output, they come as yellow and black as well. So this is how laminar flow works. Similarly, there is a lot of surface tension phenomena which you would be able to generate, you will be able to encounter when you start working with at micro domains. This is an example of an ant movie. Ant, or say a small bug, could easily walk on water or say float on water, and that is because of surface tension of at the micro scale or micro domain. So with increase in surface to volume ratios, we have large amount of surface effects, less amount of volumetric effects. As you could see, A by V varies as length raised to -1. So that's where the volumetric effects are really less as compared to surface effects. So there are large amount of surface effects when you encounter microfluidics per se, or in general microtechnology or MEMS devices. So why microfluidics then? There are the advantages are similar to MEMS devices, but then there are few with a difference of few. For example, small volume will encounter not only reduced cost, but small volume will you will be able to test your reaction rates very rapidly, because at small volume the rates of reaction increases. There are a lot of repeating units in microfluidics, which would basically decrease the waste of material, because what you are doing is you are doing any reaction at micro scale, and when it is at micro scale, you tend to go closer to the molecular domain, and when you are closer to molecular domain, you are sure of reacting molecules because the mean free path reduces significantly. We could do parallel measurements and hence have faster assay time, again because of the small size, and decrease mean free path. The rates of reactions are very high, and then you could achieve the result quickly. There is a disadvantage, as I mentioned, in terms of batch synthesis, but then what we could do is for batch fabrication, you could actually number up the technique. So if you have one single chip giving you, let's say, X amount of volume at the output, what you could do is to increase that X, you could go on increasing the number of the devices. Rather than using one, you could use maybe 100 devices, such devices. So it could be 100x times the output. So that is how people are increasing the productivity in terms of batches. But what you could kind of get is you could leverage the advantages at micro scale, having better data quality. So when you are considering an output, I think the output is extremely high as compared to the batch product or batch reactants, and so the deviance is not there in these kind of devices. So you could easily integrate MEMS into microfluidics, with silicon being a part of microfluidics, because there are a lot of research happening on silicon products also. That is, you could create channels in silicon devices, and then you could use silicon as a substrate and integrate electronics which has fluidics also. So maybe you could have a lot of things included, and then it becomes a single package, and this could become a very neat and handy portable device, which has it is fluid compartments as well as electronics on a single wafer packaging. Because of all these things, automation is obvious. So these could be then automated, and then because of automation and smaller sizes, you could have footprint to be very, very small. So once the size is small, and what we are now really worried about the X and Y, we are not really worried about the Z, that is the third dimension, which is the Z dimension. So everybody is talking about X and Y in terms of sizes rather than Z. So what you could do is if you decrease the X and Y and start building your devices in 3D, I think you are saving a lot of space in the footprint, and that's how you could have a very small contact footprint wherein the devices are functioning faithfully with smaller sizes, with high amount of integration. What is still unobserved is the single cell molecule assays, which people are trying to do. Even in my lab, we are trying to kind of culture single cells. which is highly difficult task. I won't say it is impossible, but it is very difficult to culture single cells, because cells like that coziness in terms of closeness of members. So that's where I think it becomes very difficult. And then we could then go to subcellular domains and mimic in vivo in microenvironment. And that's again we are trying to do in our lab, to culture cells and then mimic in vivo conditions in the lab space. If you are really interested, you could kind of search keywords like organ on a chip platforms. They use lab on a chip technologies for creating artificial organs on a chip, so that you would be able to test lot of parameters on those artificial organs, which are very close to the in vivo system, that is the in vivo model. So what this can offer is a lot, wherein you have laminar flows, diffusion control regimes, you could have transport of fluids, you would have precise temperature controls, you can dispense liquid in micro domains, volumes of the order of even femtoliters in cases. We can use channels, we can use electrodes, we can use optical waveguides, and there are many other advantages of integration of technologies with MEMS, that is silicon MEMS as well as microfluidics. So you could integrate a lot of components because they come at same scale, and if you are using a similar kind of substrate as in silicon, it becomes very simple to integrate different kind of devices. People have also integrated, as you saw in the earlier lecture, SU8 and Kapton as well as PMMA layers with silicon and electrode system. So there are examples, there are many examples as such of integration of various different components on a particular chip. But microfluidics is kind of bad. It's not all rosy. It is not so good at separating fluids. It's what we are trying to do in our lab, separation. And then batch processing, because what is important is batch to batch variation should be very, very less. So reproducibility as well as reliability becomes very imperative, important aspect to be remembered when we are thinking about commercialization. So going forward, this is going to be the way that's probably will be required to be solved, this batch problem of batch processing and variation with batch to batch. So if the techniques, that is fabrication techniques, are more and more mature, because currently there are so many things happening in terms of materials, in terms of application, in terms of devices, in terms of materials to be used, in terms of techniques of fabrication. There are a lot of things which are happening, and that's the reason there is no one single answer to the question. There are many answers and many possibilities when it comes to fabricating these devices, and I'm going to introduce you to one more technique of fabrication. So this is more or less a chart of various different microfabrication processes, how you could fabricate not only MEMS components. So typically there are techniques such as property modification processes, such as diffusion and ion implantation. They are typical silicon processes wherein you could implant or diffuse different kind of atoms in the silicon to change the property of silicon. So you all know silicon is semiconductor, so you could have trivalent as well as pentavalent impurity injected into silicon to have N-type as well as P-type semiconductor. Then patterning could be done by lithography. Now there are many types of lithography. What Mac showed was UV lithography. That is something or commonly known as photolithography. People are extensively using photolithography in their laboratories, but there are other techniques like LIGA, X-ray, and other lithography techniques are also being used. And out of that, template assisted lithography or soft lithography is again a very commonly used lithography technique. You could do subtractive processes like wet etching or dry etching. This is again, it comes from silicon. There are wet etching means you have anisotropic as well as isotropic, even in terms of dry etching too. So you can have isotropic as well as anisotropic etching, which could be then used for fabricating different kind of structures. This is typically done while fabricating diaphragms or cantilever beams in silicon or even in polymers. So going further, there are additive processes such as oxidation, physical vapor deposition, as well as chemical vapor deposition. And once you are done with all these processes, then what you do is you package your device, and that is a typical manufacturing protocol. So you start with a single substrate and you end up with a device, and a dice device, which then functions or even goes to quality control, quality testing, and then functions as whatever parameters we have decided for. So that is how the processes occur. So, but in my lab, because I don't have access to a lot of higher end equipments and higher end techniques, so when I joined this lab 10 years back, there was absolutely nothing. So, talking about microfabrication, lithography was kind of not there. Because this is a typical biology lab, wherein you have a lot of lab benches, lot of reagents, lot of beakers, and so on and so forth, but not many instruments. And that's where I think it was very important for me to develop a technique to sustain in this environment, which is low cost as well as which is highly functional. So I always say we are trying to build devices and techniques which are cost effective, but then we are not compromising on quality of the gadgets as well as devices. So what we started off with a soft lithography, but a modified template assisted soft lithography. So it is very simple. I'll just explain in few slides, and then I think anybody could try this kind of technique at home. So basically what we do is we start with the box, an open box, and then drill holes, punch holes into the corners of the sides of the box and attach wires. So these could be copper wires, this could be like plastic wires, nylon threads. We can attach these circular kind of structures into the box and then pour PDMS. PDMS is nothing but polydimethyl siloxane. So this is a RTV, that is room temperature curing materials, that is silicone material as commonly known. So this material is liquid at room temperature but solidifies at higher temperature. This higher temperature could be like from 60 to 150 degrees centigrade. Once it is cured, it becomes hard, and then you could easily demold it from the box. So once you demold it from the box, you could then withdraw the wires, and then what you are left here in this particular case is a micro channel. So now micro channel, the dimension of the micro channel could be any, that is dependent upon the template which you are using. So this is highly important to remember. So whatever template you use, it could be, let's say, 20 micron wire or even a 500 micron wire. So whatever you are using, you are going to get similar kind of output in negative space. For example, if you are, wire becomes a positive, and what you arrive at is a negative. So you have a through and through hole. How to test them? So this is how these channels look like. So these are some fabricated devices. These are very early devices, maybe around 10 years old. So you could actually have reservoirs, you could have single inlet, multiple outlet, and even you could have spiral channels. So a point to note here is, so I just play a video just to once I talk. So this is a spiral. How could you remember is, how could you know that once the liquid actually rises up, because of gravity, the speed decreases. So now because of such kind of unconventional fabrication techniques, you could build your devices in 3D, and then you could actually work with flows efficiently. If you want to kind of decrease the speed of the flow, you could actually have channels running in the Z direction, that is upwards, so that the speeds are low and the reactions are happening, or the molecules are interacting much significantly in this particular term. So there are a lot of advantages of this technique. And then what we could do is we could fabricate such kind of devices. Now this was because we wanted to have reproducibility in the fabrication technique. So what we did was we got in touch with a fabricator, that is an aluminum fabricator, which probably is available in and around Pune, many of them. So what we did was we got this kind of a mold fabricated, so that once pour PDMS, we should get reproducibility of the devices. So all the devices should be of the same nature, same size, same shape, and so on and so forth. So that is how what we did was we selected this kind of technique, and you could see there is a straight channel, parallel channel running in here, and you could see there are inlets which then would be able to be connected to the outlet, that is to different kind of outlet or inlet ports. So what are the features of this technique, that is modified template assisted lithography technique, as compared to conventional techniques such as photolithography? Now, this is an extremely simple process. What you require is some materials here and there, which probably every lab has. This is done in one step, and this is rapid. So within 3 hours, if you are heating it at say 65 degrees centigrade, your devices are ready in 3 hours time. If you are heating at 150, you could expect your devices to be out baked in let's say 15 to 20 minutes. So that is the rapidness of this technique. So you could have one step easy as well as rapid process. Now, the important part is because these devices does not require a bonding line. Now, if you are using a photolithography, if you want to create a channel, what you require is a bottom channel and a top lid. So in this particular process, you don't require that. In lithography, then you would require to have two different substrates to be sealed, and then you really have to work on the sealing part, that is the addition part. So in this particular case, because it is one step easy process without any bonding line, you could work with lot or large amount of pressure. So you could have pressure driven fluids, and not only very small amount of pressure, but large amount of pressures could be applied without any leaks. So that is an added advantage of such kind of technique. So as you are aware, all these photolithographic fabricated channels are square or say rectangular in nature. So the cross section becomes, let's say, 100 by 100 micron. In this particular case, because we are using wires or threads, we are very close to the natural symmetry. So all these structures are spherical or cylindrical in nature. So the channels are circular. So there is no corners in the channel, and because there are no corners, what we end up is having very easy flows, very smooth pressure driven flows without any air trapped inside. Because generally what we end up is at lower flow rates or even higher flow rates, if the corners of a square or rectangular channel can kind of generate gases and they could hinder the flows. So that is, in this particular case, we don't encounter such kind of problems, and it is very free to move liquid. We can have freestanding microcapillaries, that's what we have fabricated, and then we can fabricate microchannels at a very high or large lengths with high fidelity. So we have fabricated microchannels of cross 100 micron diameter, 100 micron, of the length of, let's say, 1 feet. So that is kind of the sizes which we would be able to fabricate. So this is purely template assisted lithography. The only disadvantage of these this kind of unconventional application process is you are dependent on the template. You cannot think without a template. You always have to create the template first before you create a device or a micro channel. We have fabricated micro channels of the order of 20 micron, but going down in sizes would be seriously difficult, because when you have smaller and smaller dimensions, then the removal of the mold, that is the template, becomes very, very difficult, and that's where we are encountering problems. But then what we can do from 20 micron to 500 micron is something which is very significant. So coming back to this goal, so what I have discussed is the fabrication of microfluidic chip. So the next in line is the recognition element. So as I mentioned in the start, there are many recognition elements like nucleic acids, proteins are being used. So what we have tried, or even in case of antibodies, are considered as recognition elements. So to detect these kind of pathogens, what is essential is we should have very specific recognition element. Now, thinking of a recognition element, it should be some entity which would be able to precisely locate and recognize a address, that is the pathogen, and that is what is very important. So in this particular case, what we did was antibodies was an obvious choice, but antibodies are again biological entities susceptible to a lot of environmental factors, that is environmental variations. So they are temperature sensitive, they are pH sensitive, as well as the sensitivity they show, that is the secondary antibodies, the sensitivity they show in detecting a particular antigen is around 70%, because close they generally miss, those antibodies miss, and that's where we thought about working with bacteriophages. Now, bacteriophages are nothing but virus-like structures, virus particles. So these are very specific to a particular host. Even in case of COVID, so COVID is a virus, it is very specific, or it binds to particular host, and once it binds, so it specifically binds to a bacteria. So when it binds, it actually pushes its DNA into the host cell, and using the nutrients from the host cell, it multiplies, and then again the whole process continues. So what is essential to remember is a bacteriophage will recognize a bacteria, a specific bacteria, precisely. So the specificity between the detection is very, very high. So that's where I think we picked up this bacteriophage, and we thought about using the tail spike protein, because the tail is where the bacteriophage will recognize a particular antigen. So it will latch on, using the tail, it will latch on to the bacteria, as you could see in this particular picture, which is a TEM image. So it will actually hold the host using its tail, and then a central portion which you could see the sheath. Here there is a DNA machinery which is there in this capsid protein. So here the DNA machinery is there, and then DNA machinery is then, after the cell membrane is broken of a host cell, the DNA machinery is then injected inside the host cell. That is how a bacteriophage will function. So what we decided was, we thought of using the tail spike protein as a recognition element because of its specificity and sensitivity. So we used a technique known as biopanning. So biopanning, what it will do is, with multiple rounds of biopanning, we would be able to generate a sequence, that is an amino acid sequence, which would resemble the protein sequence, which is the tail spike protein sequence. So once you have a sequence which is very specific to a bacteriophage, then you can, rather than using a bacteriophage, again bacteriophage becomes a biological macromolecule. So rather than using a bacteriophage, you could then use a synthesized sequence. So once you have amino acid sequence, you can synthesize a peptide, that is, or an aptamer, using that particular sequence, and then use that sequence for recognizing a particular antigen. That's what we used in this particular case. So the next in line was using magnetic nanoparticles and quantum dots. So why magnetic nanoparticles is because now we want to detect in flow. We want to detect these pathogens in fluid rather than for separating them. We thought of detecting them in fluid itself. So what we used was, we used magnetic nanoparticles because these are very simple method. There is a simple method to isolate these pathogens from moving fluid. So what we did was, we first modified the charge of these nanoparticles, because the cell wall of a bacteria is negatively charged. What we could have is a positively charged magnetic nanoparticle, which would then bind all the bacteria which are present in a sample. So once you pass a sample and then you just have magnetic nanoparticles into it, which are positively charged, you would be able to kind of capture all the bacteria which are there onto a particular sample or in a particular sample. So that is what we did. You could see an SEM image wherein these rod shapes are Salmonella bacteria, and you could see these tiny little structures which are observed are nothing but magnetic nanoparticles, which are positively charged magnetic nanoparticles. So we, with this kind of a very easy protocol, we were able to kind of isolate bacteria from a liquid sample. Then comes, how do we detect? Because once you are detecting, or say kind of capturing a bacteria, then you should some way detect these nanoparticles, or say bacteria. So what we did was, we then synthesized quantum dots. So quantum dots are nothing but fluorescent nanocrystals, which are semiconductor in nature, and they have a property of fluorescing at a particular excited UV wavelength. So all these quantum dots would excite at 360 to, let's say, 380 nanometers, which is a UV, and you could get color, that is fluorescence, depending upon its size. So a typical 7 to 9 nanometer quantum dot will give you red color, and a 5 to 7 nanometer quantum dot will give you green color. So that's what we did. We synthesized these quantum dots, and then we use these quantum dots for detecting a particular bacteria. Again, we have to, I'll be discussing in a short while how do we detect specifically these kind of bacteria. So this is a typical mechanism which we call as a capture and release mechanism, which we have designed for detecting bacteria from any given sample. I mean, this could be a food matrix, it could be a water matrix, or it could be a milk matrix. It could be kind of any matrix. So matrix doesn't matter at all. So this is a kind of mechanism we developed in the lab for detecting. Currently, salmonella and similar method, we can detect any kind of bacteria. So what we used here was three different zones, which is one becomes a capture zone, second becomes the recognition zone, and third becomes the detection zone. So that was the early start of this device where we would be able to use direct bacteriophage. So we wanted to demonstrate, or say we wanted to know if at all bacteriophage were very specific to a particular antigen. So red color ones were Salmonella typhimurium cells, and yellow color ones are other bacteria. Obviously, when you take a food matrix, water matrix, or any given matrix, there is a pool of bacteria. So there is a single type of bacteria does not really, a monoculture does not really exist. It's always a multiple pathogens are present in a sample. So what we did was we first activated the magnet beneath the capture zone. So what happened is when you pass magnetic nanoparticles along with bacteria, all the bacteria become are captured, and the fluid, which is of debris, which of unwanted material, just are passed through. So they just flow through, and whatever is required, that is magnetic nanoparticles with all the type of bacteria, are then captured onto the capture zone. So once this is captured, we then flow bacteriophages and then activate the recognition zone. So what happens is now these bacteriophages are specific to Salmonella typhimurium cells. They are very, very specific. So what they'll do, they'll bind to Salmonella typhimurium, and then because now the magnet number 2, that is under the recognition zone, is activated, these magnetic nanoparticles along with the bacteria and the bacteriophages, which then get attached only to Salmonella typhimurium, will be captured at the recognition zone. So once this is done, so what we used was antiphage antibody, which would then bind to the bacteriophage, and they were conjugated to quantum dots. So this becomes again a process. So again, the magnet number 2 is deactivated, magnet number 3 beneath the detection is activated. Once you flow in the quantum dots conjugated with antiphage antibodies, now these antibodies are specific to bacteriophages. They'll get attached, and then they'll be immobilized near the detection zone. And that's where you could detect optically, you could detect under a microscope or any other method known for optical detection. So these are all fluorescent moieties. They at excitation of 360 nanometer, you would be able to see a visible color, and the intensity of color would be the number of bacteria present. So that is how you would be able to calibrate that. So if we want to integrate this whole technique, that is having microfluidics, using nanoparticles, using quantum dots, using bacteriophages, or even peptides in that particular sense, you need a particular device. So we went on to fabricate this particular device. So we modeled this first. So these are, rather than having, if you could see, these are like on and off magnets. So rather than moving the magnets, we use electromagnets in this particular case, which would be then automated. So these were 3 electromagnets at C, R, and D zone, which represent capture zone, recognition zone, as well as detection zone. So this is the bottom layer, which is of electromagnetic unit. The top compartment is of optical detection. So we then devised the whole optical assembly, which had filter. We were trying to detect green color, so we used green color filter, which was plus or minus 10 nanometer bandwidth. So that was a very specific, highly specific filter which we use for green color, and used a avalanche photodiode as well as a normal photodiode in this both the cases. We were able to get high sensitivity of the detection. So there is a small port which has UV LED, and then there would be running, I'll just show you in the next image, with 2 fibers running to excite the nanoparticle assembly. If I could just run through this particular slide. Yeah, so if you could see these 2 tiny things here, like here, these are channels. We did insert these fiber optic probes from here, so that at the recognition zone, once there are quantum dots here, we would then pass light from the fiber optic zone, and then we would be able to detect the color intensity from the top. That is how we inserted fiber optic probes from the optical detection unit into the microfluidic assembly. So that is where in the channel. So this then whole becomes a very nice unit, which is workable unit with inlet and outlet having coming from the sample as well as waste which goes to the outlet in the microfluidic chip holder. So we can fit our microfluidic chip, which I showed you just now, in this particular holder, and this becomes a tight assembly wherein we would be able to detect. So that is how the detection process happens. So we are using a syringe pump in this particular case with loaded reagent. So we then know exact incubation times required and flow rates required. That is how everything was then calibrated previously, and then we could just pass through a syringe pump, and then you could collect the reagents. And here, when you have quantum dots, that is the last step of recognition completed, you would be able to detect using either optical microscope or optical detection unit or any other technique for optical detection. So this is the preliminary version of device which we have now kind of modified. So these are the three magnets and switches to switch on and off the magnets. So you could see this is the electromagnet unit, this is the chip holder unit as well as the optical unit. So that is how you could create the whole zone of capture zone, recognition zone, as detection zone. And then there are two inlets in this particular case for the microfluidic chip. So this is the chip which we had fabricated, and then you could have, this is the inlet coming from the syringe pump, and you could see these are liquid samples which we are then trying to inject inside these microchannels. So this becomes the inlet and this becomes the outlet, and these are the sample separated by an air plug. So you could see the transparent tubing here, somewhere here. These are nothing but air which was inserted separately so that the reaction process then runs automated. So this is how the whole thing then gets assembled. And then you could have specifically zones coming. The magnetic nanoparticles actually get captured on specific zones. So this is how the whole chip will work. And then this is an optical unit, as I was mentioning. This is the fiber optic probe. So the light was coupled from a UV LED to a fiber optic probe, and there you can see there is a tiny vibrator inside the optical assembly. Now, vibrator is important part of the whole assembly, because what happens is the magnetic nanoparticles tend to aggregate. So what we had seen earlier was, if we do not tap the microchannel, because of the aggregation, the efficiency of the detection was drastically reduced. And that's where we thought of integrating a very tiny vibrator in this particular cassette, so that it will impart slight vibrations, so that magnetic nanoparticles will then dislodge, and we would increase the sensitivity as well as the capture of pathogens. You could see in this particular slide, this is the photodiode and this is the UV LED which are inserted, and from the UV LED, the fiber optic probe couples the light onto the microfluidic channel. So this is the APD, that is photodiode, and a UV LED, which becomes the complete assembly. So in that particular tube, beneath the APD, we have all the components required for collimating the light onto the APD, which comes from the quantum dot. So you could see these are the air plugs, and once you start the syringe pump, the liquids start flowing through and then separated by the air plug. So we could actually have all the reagents preloaded in the microchannel, and what you collect is just the output, and that is how all the assembly could be then you could think of running complete assembly automated. So this becomes a very important way to generate a particular automated device. So as I was mentioning, this is just to give you an idea of what is the size of the device. So these are the three zones: capture, recognition, as well as detection zone. You have optical assembly, wherein you have all the optical components, a vibrator to dislodge the magnetic nanoparticles, and a fiber optic probe. So the probe actually runs from here and gets inserted into this particular space, which then illuminates these quantum dots to have fluorescence. So that is how the whole assembly actually functions. So this is the way fiber optic actually couples the light, and then you could detect fluorescence. So these are the results obtained from this particular device. So what we have done is we could then detect cells of the order of 10 CFU per ml. So you could see that this is the standard curve which was generated, and then we varied the concentration of bacteria from 10 raised to power 1 to 10 raised to power 6. Because why we restricted ourselves to 10 raised to power 6 is anyway 10 raised to power 6 is a very high load, and if there are these amount of bacteria present, then anyway the sample is going to be very non-potable. So these two organisms which I was talking to you about, Salmonella as well as E. coli, these are both are zero tolerant organisms. So the convention says that even if one organism is present, that is, for example, in case of E. coli, even one organism in 100 ml sample volume is non-potable, it's not drinkable. So that is the sensitivity of the detection which is required, and that is what we are trying to achieve in this particular case. So this becomes a standard curve, a calibration curve. So what we could achieve was nothing but we generated a standard curve using the spiked sample. So we have sample and we then added known concentration of bacteria. So you could generate a curve which was from 10 raised to, this is the control, which is not, nothing but the only sample without the cells. And you could then start flowing through cells from 10 raised to power 1 CFU per ml to 10 raised to power 6 CFU per ml. We could detect as low as 10 cells, because you could see there is a difference between the control as well as the signal, which is around 10 cells. So the whole assay which I was just trying to show you in this particular slide, which is the video, the complete assay took around 27 minutes as compared to the conventional, which takes around 24 to 48 hours. So this is a significant reduction of time as well as sensitivity. So you could see that there are only 10 cells in this particular case which were detected. For this particular chart, I don't know why, but always there was a problem with the cell number 10 raised to power 5. I don't know, maybe there is some magic or something. We always used to get low intensity in sample with 10 raised to power 5 CFU. So we just thought of leaving it as it is, as a deviation to our research problem, or say the technique. So this whole thing then runs unmanned, automated, and what you get is around 10 CFU per ml as a limit of detection in 27 minutes. So we thought of using spiked milk sample. So with spiked milk sample, because the matrix is now white in color, what happens is there is noise which is then created in the microchannel. Hence, the limit of detection gets pushed up. So now what we could detect is around 10 raised to power 3 cells per ml. Total assay time again same. We did not actually have a difference in the total assay time. So you could see this is the preliminary version of the device. What we did was we then shifted on to the synthetic part. That's what I was mentioning, because as you could see, the limit of detection also decreases when you are using a matrix, because we are using biomacromolecules. So there are two biomacromolecules being used in this particular case. One is a bacteriophage, which is a virus-like particle, and secondly, an antibody which is specific to a bacteriophage. So both, if you could eliminate, then we would be able to then display the assay in a complete synthetic manner. There won't be any biomacromolecule, hence there won't be any deviation from the data. So the results would be then more accurate, as well as we would be highly specific as well as sensitive in terms of detecting these kind of molecules, or say bacterial pathogens in this particular case. So when we introduce synthetic chemistry to simplify the whole model, we had to kind of make certain amendment changes in this particular scheme of working. The capture release mechanisms remain same. The capture recognition as well as detection zones again remain same. What we now use in this particular case is rather than having bacteriophages, we use peptides as recognition elements. So the blue colored ones, if I have the scheme, yeah. So the blue colored ones would be then replaced by peptides in this particular case. And we could use avidin biotin chemistry, which is a very well documented, very well established technique for conjugating, or say for detecting specifically a particular molecule. So that's where I think two variations were done in this particular whole scheme of detection. And we then got our peptides from bacteriophages using a a biopanning technique. So this is the technique of biopanning. So this is a bacteriophage. So what you could do is you could assess the binding of a bacteriophage to a substrate, and after washing, how many bacteriophages are binding. So what happens is you just go on in completing number of rounds to attain specificity. So what we did was we had around 5 rounds completed for attaining highly specific bacteriophage, which was specific to first E. coli as well as Salmonella bacteria. So both the peptides which we have designed or derived from bacteriophages with this particular process known as biopanning. So this data is for Salmonella typhimurium. So you could see these are the peptide sequence which we obtained, 4 of them with high frequency of occurrence from 45 to let's say 6%. And you could see that PEP49 shows extremely high sensitivity. So this is very specific peptide which was derived from tail spike protein, that is protein of a bacteriophage. So that is the reason this is very, very specific. To assess the specificity of this peptide, so we assessed through intraspecificity. So you could see we took species of Salmonella. So Salmonella has various species, that is Salmonella typhimurium, Enteritidis, Aboni, Typhi, Aureus, so on and so forth. So this was Salmonella species, and these are other bacteria. So we have Vulgaris, we have Soni, we have E. coli, we have Subtilis, and so on and so forth. These are other bacterial types, and these are Salmonella species. So it is intra as well as interspecific. You could see a high amount of signal for only Salmonella typhimurium, which indicates that this is very, very specific to only Salmonella typhimurium. Neither that Salmonella species nor other bacteria. The other bacteria does not even come into picture in terms of the absorbance value, which was detected at 450 nanometers using a nano drop technique. So you could see that PEP49 was found to have high specificity for Salmonella typhimurium. So what we did then was again the same assay. Now in this particular case we used the peptide. So the scheme was then modified. Rather than using bacteriophages, we have peptide in this particular case, and what we did was the peptide was attached to then quantum dot using Abiding chemistry. So rather than using the antiphage antibody, what we have is streptavidin coated onto the quantum dot and Avidin tagged peptide. So we have one end which was tagged with Avidin, that is biotin, and then one was streptavidin was coated onto a quantum dot. So then biotin as well as streptavidin will interact and bind to itself to give us the signal. So that is where this whole assay was then performed, and what we got was you could see that the limit of detection was decreased from 10 raised to power 3 to 10 raised to power 2 in this particular case for milk sample. So again, assay time was same, but then we got very high specificity. So if you could then just recall the earlier slides, the error bar was very high. So in all these cases, error was very high, but when you come to bacteriophages, you hardly have any error in detection. So that is where I think we are more sensitive as well as specific towards detecting. So we can detect 10 raised to power 1, but then we are not very sure of 10 raised to power 1, but 10 raised to power 2, that is 100 cells per ml are reproducible as well as repeatable. So we could get 10 raised to power 6 very routinely. So what was the next in line was miniaturizing the whole electronics, because the previous version of electronics had wires on a general purpose PCB. So we did manufacture the PCB as well as the microcontroller in this particular case, and then fabricated everything that is the signal processing as well as detection systems on a single PCB. So this is the UV LED which we have used, and all the detection filters are here, that is the electronic filters are here, and this becomes the microcontroller to perform the whole assay automated. So this was an attempt to build the whole device, and now you could see that we can actually detect 10 cells per CFU and the assay time was 15 minutes. Now why this assay time was decreased? Because in this particular case we can use high power electromagnets. So just by increasing the power, the efficiency of detection, that is the efficiency of capture of magnetic nanoparticles, was increased. And because we are now doing a complete automation, and then the vibrator is not continuously on, can start and stop vibrator when the magnetic nanoparticles are in flow, only then the vibrator was switched on. So doing all these necessary tweaks as well as tuning of the device, which includes electronics also. So with this whole thing, we could then push the limit of detection down to 10 cells per ml, and the assay time to half, from 27 minutes to roughly around 15 minutes. And that is the whole device which we have fabricated. So this is kind of a functional device which we have in place. Again, we have not commercialized. We are looking at commercial partners for giving out this particular device. But then the whole point of fabricating this device, this does not stop here. So I have an ICMR project on detection of multiplex pathogens. So what I demonstrated in this particular case was only for Salmonella and E. coli independently. So all these graphs are for Salmonella using this particular device. What if we have to do multiplexing? And that's where I think we are now heading towards. So this is again a calibration curve from a complete device which uses Raspberry Pi as a control unit. So you could see that we can have a calibration curve as well as a validation test, wherein we would be able to then detect 10 cells per CFU. So this is, we have named this device as bug sniffer. And you could see all the points which we started off with. The necessary conditions, that is the necessity of having a detection device which was highly imperative. Do we meet those conditions? So when we assess them, yes, rapidity was definitely achieved, wherein we were able to detect the device with high flow rates, so that the assay gets completed in around 15 minutes. So when we compare the detection to 28 hours or 48 hours, which is a conventional technique for detecting bacterial pathogens, we are very, very ahead in terms of rapidity of the device. Do we have sensitivity? Yes, we have sensitivity in detection, but we can push this still further. The sensitivity currently is around 95%. Let's say 90 to 95%. We can still push this further by including specificity as well as more electronics, that is very specialized electronics. We would be able to do, we can take the device or increase the sensitivity of detection in the device. Do we have reliability? Currently not. We have to test millions of samples, I mean minimum thousands of samples when we are trying to assess the reliability. Currently at lab level, we are able to kind of prove the reliability of this particular device. But when you talk about commercialization of this particular device, we need to assess the reliability in multifolds. Portability, yes, it is portable, but we can still significantly reduce once we have everything on a single PCB. So currently the electronics is still in a developmental stage. Once we freeze the electronics, we would be able to fabricate everything on a single PCB, and then it could really be a portable device. It is robust, yes, it is robust, but the robustness as in can be increased further once we have a portable unit. Is it reproducible? Yes, it is definitely reproducible, because at a lab level, we have tested it multiple times and we are getting similar kind of results every time we test the device. Is this device cost effective? I think in all terms, it is cost effective, right from the fabrication of the chip, the electronics, because what we have used is all general purpose electronics component which we have used, and that is the reason we could say in all respects, this particular device is cost effective. Is it easy to use? Not so much. What I mean from not so much is currently any layman, that is any consumer, cannot use this particular device. It still needs some level of expertise for injecting samples or even detecting in certain cases. That is the reason I would say this is easy to use, but again, not so much. But then there was one more part in this particular thing which was left, which talks about multiplexing, and that is what we are having in this particular project of which is sanctioned by ICMR. Now, as you all know, there are many bacterial species. I mean, there is outbreak of one, but then generally the outbreak of the other is ignored. And that is where I think it becomes very, very important to detect multiple species. This is in terms of bacterial pathogens when we are talking about food as well as waterborne matrices. What about antibody kind of testing? For example, we are all aware of MDRs, that is the multi-drug resistance. So you encounter such kind of problems of multiple pathogens, that is outbreak of multiple pathogens, or even in case of detecting a sensitive or maybe a specific antibody which would be specific for you, that is the susceptibility testing of an antibody. So in this particular case, what we need to do is we need to detect pool of antibodies or pool of pathogens. So I think that becomes very essential that we do multiplexing of this device. So testing of single pathogen is good, but if we could do in the same time multiple pathogens, I think that becomes next level. That is, we actually change the whole commercial model, because now we can test multiple pathogens in this particular case. So the first challenge in this particular case was to detect Salmonella as well as E. coli. Now what we have is, using the biopanning technique, we have peptides for both the pathogens, that is E. coli as well as Salmonella. So what we now need next is, currently in this particular device, as you have seen, we because we are using magnetic nanoparticles which are positively charged, we are kind of capturing all the bacterial species. And because we are capturing all the bacteria, the sensitivity becomes an issue, because whatever we say, these peptides probably are slightly specific to Salmonella species. They are maybe negligibly specific to different kind of species of other bacteria. That is, if we are talking about only specific to Salmonella, it might be slightly or negligibly specific to S. aureus or other bacterial pathogens. So that is the reason we are kind of getting less sensitivity in this particular device. So what is then the way forward? The way forward is to separate these bacteria initially. So currently what is happening is, we are detecting, or say we are isolating a pool of bacteria, capturing a pool of bacteria. And once we kind of capture the pool of bacteria, then only then we are able to detect specifically. But in our device, in our chip, we already have multiple pathogens there. So the way forward is to remove those pathogens which are unwanted. So if we don't want other pathogens, they ideally should be removed from the chip. So rather than having a magnetic nanoparticle which is positively charged, what if we have magnetic nanoparticle conjugated to a particular peptide which is specific to a bacteria? And that is what we actually did. So this was the research carried out for E. coli. I have shown you the intra as well as interspecificity of Salmonella. This is for E. coli. And then what we could do is, once we have proven the specificity of E. coli as well as Salmonella, we use these two peptides, that is the amino acid sequence of these bacterial species, which is Salmonella as well as E. coli, and conjugated to magnetic nanoparticle. So here then it becomes a separating chamber. So what we are doing is, we are inletting two different magnetic nanoparticles, which is one conjugated to E. coli peptide, and second it is conjugated to Salmonella peptide. So once we have these two separate magnetic nanoparticles highly specific to capture a particular bacterial species, then what we could do is, we can separate the bacterial species from the pathogen, or say from the pool of pathogens. So if we are kind of inserting here sample from one inlet, and then E. coli specific peptide conjugated to magnetic nanoparticle from the other, what we have is, in this particular inlet or in this particular chamber, then what we are having is E. coli is only and no other bacteria, and that is what we did. Similarly, what we could do is for Salmonella, and once we could detect specifically these two peptides, then we conjugated again with quantum dots to have fluorescence signal. And what you could see now in this particular chart is a multiplex detection. it is a multiplex detection, meaning we could actually then detect two bacterial species simultaneously and with high fidelity and high specificity. In this particular case, now we don't have other pathogens interfering in our signal, and that is how you could achieve a particular pathogen. And this is the device which we actually run, and we are using multiple syringe pumps to flow in magnetic nanoparticle conjugated peptide of E. coli specificity, of Salmonella specificity, and samples. So this is how what we are targeting, and followed by LAMP assay. So further in the development, we are going to use a nucleic acid based detection to increase the sensitivity of this device so that this becomes very well accepted in commercial space. So thank you for patient listening and a long talk, and I should not close this session without acknowledging the funding support from ICAR, from Department of Science and Technology, that is Science and Technology, and Ministry of Science and Technology, as well as Nanomission and SERB. So all were instrumental in developing such kind of projects or other projects which I am running. And again, I should really thank the bunch of students coming from varied disciplines. Some are electronic engineers, some are electronics, masters in electronics, some are biotechnologists, some are microbiologists, some are zoologists, and so on and so forth. So I should thank everyone before I close down. So I'll open this for question and answers, if any.
Okay, there are several questions that we have already received from the participants. I'll start now. So first one is, what is a negative space? You said something like negative space in your talk. So someone has asked, what is a negative space?
Can I ask in what sense?
I don't know. This is the question. Let us go to the next one. In what way microfluidics can be used in drug delivery module?
Okay. In drug delivery, for example, you can conjugate your drugs with nanoparticles, and then you can inject. So for loading those drugs, so for example, you need precise concentrations and precise volumes to be loaded when you are using it for drug delivery. So to precisely load drugs onto nanoparticles or carriers, so whatever carriers might be, you can use microfluidics that particular sense.
Okay. Which material is suitable for the box?
Any material.
Okay. How you are defining the separate zones?
They are defined by the magnets which we are using. So because there is a specific magnetic field attached to the magnets, currently we are using electromagnets. So we have defined, we know the magnetic field lines of force where they do not collide with each other. That defines the separate zones. So that is how we have done, we have defined zones.
Okay. The next question is there any MEMS open source software available?
In terms of, again, what? If you are talking about simulations, there are trial versions available, but there is nothing like open source software.
Yes, and I will answer this. In this Lab on Chip workshop, there are going to be some demonstrations and talks on this design software for microfluidic chips and MEMS. So I think you can hold that question for a while. Okay, I think that, okay, one more has come. Different cost-effective fabrication methodologies, what are these for making microfluidic devices? Cost-effective.
Soft lithography is the most cost-effective of all.
Okay. So I think we are through with the questions of the participants. On behalf of participants and coordinators at DIAT, I again thank Dr. Dhanajay Bodas for a very detailed and illuminating talk. It was very exciting to see that he has actually made a device starting from the basic designing aspect of the microfluidics. So this is really commendable, and he has very well explained how this LOC topic is completely multidisciplinary. So let us again thank Dr. Dhanajay Bodas, and we will end this session here. We will again meet after lunch at 2 o'clock. So I'm ending this session now, and let us all again meet at 2 o'clock for next lecture. Thank you very much.
Thank you.
Huh?